Okay, we're gonna get started if everyone's ready. Good afternoon. My name is Kelly Sexton. I'm the founder of the Med13l Foundation. Super excited for today to hear our Med13l talks. We have a great lineup of presenters, and I'm going to go over those with you real quick. First, we're going to hear from Nick Seaver, fellow Med13l parent, and as many of you know, Nick, alongside the Diaz family, has taken the responsibility of moving our research efforts as an organization forward. So he's going to give us some updates. Following Nick, we're going to hear from Dr. Wendy Chung from Simon Searchlight to give us an updates on all of the data collected from our rare disease group. And after Wendy comes up, we're actually going to do some Q&A with Wendy because she has to hop over to another rare group to do another presentation. Following Wendy, we're going to hear from Chad Grueter from the University of Iowa, and then we'll take a short break. When we return, we'll hear from Rna Strich from the University of Rowan. And at the end of that presentation, we'll ask all our presenters to come up and we'll have Q&A. So you'll have a lot of time to have your questions answered. And before we get started, I just wanted to remind everyone that we also have a virtual attendance today. So we want to say hello to our virtual attendees and thank them for their participation as well. So with that, we're going to get started with Nick Seaver.
Thank you, Kelly, and thank you, Simon's Foundation, for organizing this. This has been the most amazing couple days so far. I can't tell you how grateful we are as an organization and impressed with what you all have done. So I'm going to give a quick overview of what we're doing within the Med13l Foundation and specifically the Cure Med13l initiative. Our mission, as I think you know, is to advance medicines, make them accessible to our community, and ultimately to deliver a cure. And I know that sounds kind of crazy, but in this day and age, that is actually a goal that may be achievable and hopefully in the not too distant future. So the way we think about what we're doing at the Cure Med13l initiative is really building momentum on a flywheel. We have a lot of different activities, and what we're finding is we improve and progress in one area, it helps another area, and you kind of get a flywheel going, ultimately to make Med13l a very easy and attractive area of research for academic and biomedical researchers, ultimately, again, with a strong focus on not only understanding the disease, but also really driving towards making medicines available to the population. Just a couple of quick things. One of the big things that we're doing is generating public awareness. I think, as many of you know, thanks really in large part to Kelly and Lacey, if Lacey could raise her hand, did a fantastic job raising awareness around Med13l for May 13th, which is now officially Global Med13l Day. So I want to take you through a few things that we've been focused on this year. The first is getting something called an ICD-10 code. So what does that mean? That's a code within the CDC and then ultimately globally within the WHO that allows a physician, when they identify that a patient has Med13l, to put a specific diagnosis code attached to the patient's medical record. And that does a whole bunch of things for us. This graphic on the left is illustrative of how few people in the world and in our community in particular have actually had their gene sequenced. And of course, you can't be diagnosed with Med13l unless you've had your genome sequenced. And so, with this diagnosis code, among other things, we can hopefully get onto gene panels, encourage more people to get tested. We also make it easier for physicians to understand the condition, understand how to treat it, improve patient care. This can help with insurance, And, of course, the overarching goal with all of this in driving academic and biopharma research. And, we've been in long discussions so far with the CDC, and I want to send a special shout out and thank you to Wendy Chung, who is force of nature, who took us under her wing in this process and has been absolutely incredible in driving, hopefully towards a successful outcome this fall, when we have the official meeting. I also want to thank the Hogan Lovells team, identified by another force of nature, Vanessa Diaz, who have donated their time pro bono to us, without whom we would never have thought this was even possible. So stay tuned, but we're really, really hoping that in the next year, we will actually be an officially designated diagnosis code, which would be a complete game changer for this community. I'm hoping to stand here in the not too distant future and have an auditorium filled with families wearing these t-shirts because our patient population is growing. A second key goal includes a whole variety of research and development tools that we're working to coordinate and make available for researchers. Mouse models, when we connected with Dr. Grueter, whom you're going to hear from later today, he was able to identify that he actually has mouse models that are accessible to the broader research community. We'll talk a little bit more about some of the new ones that are being developed. We are organizing the patient community in a number of ways, obviously here in Baltimore, and more recently on the Mighty Network, for example. If anybody here is not on the Cure Med13l Mighty Network, we would really invite you to join. Patient Registry, again, thank you, Simons. Patient Cell Lines, again, thank you, Simons. And then also with Rarebase, Omid, if you could raise your hand. Omid is the COO of our partner Rarebase, and among the many great things they're doing with us is developing stem cell lines from blood cells, which can be differentiated, for example, into neurons for testing. Some additional focus areas include the development of a natural history database, which is really important in a whole bunch of ways, including for clinical trials to understand the trajectory of the condition, and hopefully with some of the therapies that we're going to have available, perhaps even in the early part of next year, we can actually see the trajectory of development change in meaningful ways. But you can't see it if you don't have a baseline. And a natural history is really critical in that way. And so we're really going to launch a campaign this year to try to get people to get involved, to help us get data and understand the condition better. Related to that is something called endpoints, which has to do with how you measure success or failure in clinical trials. Getting that right is critical. Other preclinical models beyond mice, and then very important things, supporting academic research, including some of the wonderful folks that we have here in this room and on our SAB. Speaking of the SAB, I wanted to, really first make a first announcement of our SAB, our Scientific Advisory Board. Again, I have to thank Vanessa, who has done an incredible job of connecting with all the folks on this slide and bringing them together. This is a world-class Scientific Advisory Board, and many of them are in the room. Dr. Chung, Dr. Grueter, Dr. Strich, and I don't know if Dr. Bain is in the room right now, but she's here at the conference, and as well as Dr. Asadulahi in Switzerland, Dr. Nagata in Japan, Nadav Autav in San Francisco, and Dr. Gurnett in St. Louis. So this is really a global and amazing scientific advisory board who are helping us as we move forward. I wanted to take a moment and talk about what we're doing with Rarebase in relation to small molecule therapy. I think, as many of you know, Rarebase is doing what are called high throughput assays on over 4,000 drugs, small molecules, and trying to find drugs that can improve the disease by upregulating the Med13l gene and its expression of the Med13l protein. And we just had a few weeks ago our first initial readout where they shared data on over 1,000 drugs, and it was an extremely positive readout. And let me just take a moment and talk about this illustration on the left. This is not Med13l, but it's illustrative of the kind of data that we're getting from their platform. What this does is, for all these dots here, which represent a molecule, is is indicative of how much it changes a certain gene. So increase in or decrease in protein expression, and then the statistical significance of that change. And from that, what you're really looking for is the dots that are off to the right and in the upper right-hand corner. And in this example, you can see the scale on the bottom goes only to 2.5. I think ours goes to 6 or 7, which is suggestive of how many drugs we have and how many and how strong they are at upregulating the genes. So we're really hopeful when we get our full readout in September that we're going to have a lot of options for candidate molecules that we want to move forward on with validation to develop a clinical package. And our goal in the first quarter of next year is to have drugs that can be prescribed off-label by our clinicians with this validation package that can transform the trajectory of this disease. So it's beyond anything we would have hoped for even a year ago. Thank you, Omid and team. Thank you, Rarebase. And thank you, community, for all you've done to develop cell lines, donate blood, and also make contributions to make this possible. We're also playing the long game and looking at gene-based therapies. There are a number of different modalities that are really kind of the cutting edge of medicine these days. Gene therapy, gene editing, for example, if you've heard about CRISPR, and RNA-based therapies like mRNA, which we're all familiar with from the COVID vaccines, and so-called ASOs, antisense oligonucleotides. Just a couple of highlights from recent activity. We want to thank Jackson Labs, a world-recognized clinical research organization that has donated to us 3 mouse models, including so-called humanized mice, which means that their Med13l gene is spelled exactly the same as the human version of that gene, which means that gene-based therapies can use those mice to test their efficacy and safety on mice, which is a critical gate that we need to pass through as we bring true gene editing and gene therapies to our population. We're engaged with some world-class folks. Again, I have to thank Vanessa, who reached out to a number of labs, and arguably the world leader, one of the top world leaders in this particular area, Dr. Liu and his group, are fully engaged with us. And when we get these mouse models, hopefully we'll be able to work with them on something that goes even closer to the root of this condition. So with that, I just want to thank everybody. Again, thank you, Simons. Thank you, community. And we look forward to answering any questions.
Thank you, Nick. I think we're going to move on quickly to Dr. Wendy Chung because she has another room. And then at the end, we'll have some questions for you. Thank you so much. Thank you.
There we go. Okay, so very glad to be with you here today. I'm going to take off where Nick left off in terms of talking about some of those data from Simon's Searchlight. I know some of you saw me yesterday, so I won't go over some of the things that I went over yesterday, but just to say that we're, as a community, I hope, learning together and informing both the care for today and the cures for tomorrow. I think there are things that we can learn from each other in terms of until we get to the point that Nick was saying about the cures. So just to understand, you're powered by a lot of people behind the scenes. You've seen some of them out here at the registrations desk, but there are many people at home working on this and many scientists, as well as at Safari, at the Simons Foundation, as well as those scientists that you already know who are here and funded. And so just to let you know, we've been at this for 12 years and we're going to be at it for a lot longer in terms of doing this. We're not going anywhere because we know there's a lot of work to be done and we're right there behind you. Within this, I also want to be clear that this is not one and done. So the expectation, because things change over the life course, we need to continue to learn together in terms of how things are going to change. And there are different critical periods in life, I think, that are going to be critical in terms of teenage years and adolescence, for instance, as we get to transitions to adults. And I think we're relatively deficient in terms of our understanding once we get past the age of 20. And our kids are going to grow up in terms of beyond that. And so we need to prepare for that. As we do this, it's helpful for us to see the same person over time. So to see and to hear from you what happened in terms of COVID, or what happened in terms of new therapies that you tried or new medications, and understanding and integrating that information. And as we get better ways of measuring things, we also are going to try some things beyond just surveys that you're doing online. And at some point, we'll see how scalable this can be to collect that data in your homes without too much, I think, distraction or too much burden on you. As you've been hearing about from all of this, and just as a reminder, if anyone hasn't signed up but wanted to sign up, we've got the stations out here. If people have signed up for Simon's Searchlight and you feel like you're stuck, or you're not sure if you finished everything, again, folks outside here in the entryway can help navigate the system or help get you oriented to what may be a little bit opaque. So as we're doing this, we want to make sure that it's transparent in terms of this and that you're getting the most out of this that's possible. I said this before, but just to be clear, the researchers that are here at the meeting, as well as those who aren't at the meeting, are seeing your information de-identified. So in terms of privacy, I don't want anyone to be concerned. We don't sell the data to pharma, so none of this is something that the foundation makes any money out of or anything like that. And our goal is to be able to minimize the burden for you so that you don't have to do those same surveys over and over and over again, that multiple people can learn with us and benefit from everything, both the information as well as any of the cell lines that I'll be talking about. We also know that you need to learn. You need to learn as quickly as we can. And so we're giving information both about your individual person and your family. So if you fill out one of these surveys and there's information that in a standardized way can help your child with their IEP, with their neurology or developmental pediatrician or anything else, you're getting reports that go directly back to you, but can be shared with your providers or your educators. And as well as we're doing all of this in terms of being able to, in the aggregate, see how the group is doing. And again, no one's identified by name in those aggregate results. Things like today, and we've got video cameras going in the back so that these are posted online. That includes any of my slides today. You're welcome to take pictures, by the way, but this is all going to be posted online so that if there's anything where you say, I don't know, that went by a little fast, that Dr. Chung, she speaks really quickly, and you want to hit the rewind button, any of this is available for rewind. You can share it with any of your child's providers. And for anyone new in the community who wasn't able to, or anyone in the community not able to come today or be online, or new people as they onboard, all of this will keep available on our website. Just very briefly, some of you have been giving blood samples upstairs. I know that's not easy, but one of the things that's done with the blood samples, as you've heard about, is to be able to make those iPSCs that Nick was talking about. I'll just say that we do that, again, de-identified, but we make that at significant expense actually to us to be able to share with researchers around the world so that they can then study your child, your loved one, with brain cells in a dish without having to do a brain biopsy, right? And so that's great in terms of checking some of these treatments, as Nick was talking about, those high throughput drug screens, that then is available to sprinkle those drugs in terms of those cells in a dish and see, are we in fact bringing up Med13l expression, and is it working? And in some cases, is it toxic? Is it doing anything bad? And so the more people we can have represented within this, the more that we can make sure that it's going to work for hopefully everyone, or at least those individuals we have represented. So it's a great way to kind of be a multiplier. One little contribution that you make multiplies in terms of the impact for the scientific community. So I'm going to start out by something that we started relatively recently. And within all of the slides that I'm going to show you, I will point out how many people are included. So for this one survey, it was based on 18 people. The limitation is it's based on 18 people, but it's just based on 18 people, right? And so if there was any, particular bias in terms of who filled out the survey, that bias will be reflected within this. One of my personal goals is I want to make this as easy for people to do as possible and try and get the numbers up in terms of doing this. As Nick was talking about in terms of trying to develop treatments, we have more interest the more people we have. The more we're counted, the larger sort of our community is, the more likely it is to get more researchers interested in this. So let me start out with the good news. The good news is that when we think about health, again, and I'll go through this in detail, the majority of individuals are in good health. And I think that's likely to be true. This is not something where I'm expecting people to go downhill when they hit their 20th birthday. We're not seeing terrible heart disease or diabetes or cancer or things like that. As I'll show you, it's somewhat limited that we only have a small number of people still, and we don't have everyone across the life course. But I think this is mostly a brain and behavior condition, not surprisingly, right? And I think though the more that we're confident that that's the case, at least we know where to focus our energy. So that ends up being important to know. Within this, I'm going to point out some of the positives mostly, but also some of the things that I think we need to focus on. Most of the community, folks are sleeping well. And I point this out because I think good sleep is a foundation basically to a good life. And although most people are sleeping well, we do have a significant fraction for whom it's an issue. And I think that's an opportunity in terms of being able to help improve something. But when I think of, if you get a good night's sleep, you're in a better mood, behavior's better, education, you're able to absorb things. And for those of us who need to take care of those individuals in the middle of the night when they get up, it's also easier for us the next day when we've had a good night's sleep. And so this ends up being, I think, an important sort of interim or intermediate goal that we can do in terms of improving sleep. In general, folks are energetic, and I see the energy bouncing out in the halls here, but they're in a wonderful way. They're energetic and full of life and full of joy. And you can see it in terms of, again, just in the hallways as we're out having meals, just joyful individuals, smiling, giggling, full of energy. And I think that's the good thing, overwhelmingly in those areas. And again, enjoying many different types of things. And it's again, to be able to increase that joy, increase that just vitality and be able to allow people to be the best that they can be. We also, because the Simons Foundation also thinks a lot about things that are around family and friends and social dimensions, mostly good in terms of being able to make contact, make friends, have interactions, but some limitations. And again, I think things that one can, to a certain extent, help with teaching, but other things that I think we need to continue to work with. And then in daily life, being able to take care of oneself and do activities of daily living, some, but still improvements. And I put it out there as a challenge for some of you that either yourself or friends or family, I think technology is our friend here. And I think increasingly as there are more technologies that allow for more independence, there are ways of being able to improve this simply by using some of those tools better. And so I think that's something that we're looking for across, for instance, the conditions we've been having here at this meeting. Okay, let me go directly into some of the more medical issues. And again, I'm going to show you by the numbers so you'll know how to think about the data. So we started out with, I always have 100 as a magic number. So we're getting close to that magic number of 100 individuals who have signed up. We're very rigorous in terms of being able to check and make sure everyone belongs in this club. So that's why we ask you guys to give us a copy of your medical genetic report. Make sure that Med13l is the right one. I'll give you just an example that you'll realize is sort of a common mistake is that there's a Med13 and there's a Med13l. And sometimes people get confused and they join the wrong club. And so we have to redirect traffic a little bit. And it's important to make sure that we've got the Med13l community here. So this is the first step in terms of doing this. I know there's a sort of gap here, and this is one of the things we need to be able to help communicate out to everyone is that you're not done just by signing up. That's not the end of the show. But the first major point is to make sure you're in the right club and then to start in this process in terms of providing the medical information. This is a big gap just for those of you who are family leaders that we need to fill is this drop off here in terms of even people who have provided their genetic test reports, they haven't necessarily continued on. So again, the messaging that we're trying to clarify in terms of, so what is it we're asking you to do and being able to help get people along that journey is one of the things we're centrally working on because we know it's confusing. And again, I just want to emphasize this is not a one and done. This is something we're trying to go back to people in a very sort of not burdensome way, literally just a few minutes every year to be able to get an update and see how things are doing and have an option to do that online in multiple languages for people around the world. For individuals who would like to, at this initial step up here, speak with someone, we also have an army of genetic counselors, multiple time zones, multiple languages, there to be able to talk to people. So it's not just a one-way street, but being able to give information back as well as to help aggregate data. Okay, this is really for the researchers, so I'm not going to spend much time on it, but just to say that in terms of those iPSCs that Nick talked about, we increasingly are building that library to be able to contribute. To a certain extent, we think about these as, although they're different genetic variations at a functional level, having the same impact, although we also are trying to take into account some that might be a little bit different so that researchers can also look at some of those less common genetic variants. And again, for any of the researchers, basically freely available through Safari Base if anyone's listening on this later and wants to be able to order any of these. Relatively easy to be able to get and to use these. This is something that for you all, you don't need to focus on this, but for any of the researchers, especially who are interested, these are the genetic variants that we have so far within these 57 individuals. And most of these behave, we think, in relatively the same way in terms of being acting as if, even though there are 2 copies of the gene, acting as if only one of those copies is working. And so giving half the amount of Med13l protein. And that's the way that we think mechanistically, or the way that we have an impact either from these or from these. We think of them mostly as being similar, subtle differences for a couple of you geneticists out there, but increasingly and important, there are some other different types of genetic variants that are very subtle differences in spelling. And these are also important to make sure we don't leave anyone behind. I am going to make the point, though, that although I said in general we think about these as being similar, I don't know that for a fact for all of these. And there may be subtle differences between some of these and some people who have these. And everyone really needs to be counted and represented, because if there are differences within this, we could end up leaving groups behind. And I don't want to do that. It's really important to me that everyone, if we come up with treatments or as we're testing treatments, that we don't leave anyone behind as we're doing this. And so again, stand up and be counted and invite your friends as we go through this. Again, as we're doing this, this is, I think, more of just the same. So I'll actually skip over this. That was just a continuation of the last one. And for those of you that are sort of visually oriented, this is just showing a distribution of where they are along the gene. And in certain cases, there may be importance to where they are exactly within the gene. And again, for any of you that want to dig into this, I'm glad to give you copies of the slides, or if you didn't get a chance to snap a photo. This is just in terms of a fancy 3-dimensional structure for some of the scientists who care about that, and I can go over that in terms of some of those interesting points. Let me get, though, into what I think most of you are here about to listen to, and this is what we've learned from a medical point of view. And this is, again, based on 28 participants, equal males and females, and 28 is good, but it's also somewhat limited in terms of just being 28, so just keep that in mind. An important point in terms of the limitations is here's the age here on the x-axis, and this is in years, and these are the number of individuals for each age category. And the important thing, which you can just visually get right away, is most individuals who are represented, at least in this data set, are less than 10 years of age. So this is basically almost all a prepubertal group and young children in terms of doing this. We do have a few adults, and that's fantastic because it's really important for those individuals who are kind of telling us what's ahead, what to be aware of, what to be mindful of. But to a large extent, our community is young. That's not surprising, in part, as Nick said, because you need to be genetically tested to be able to get your diagnosis and to get counted. But it is important for us to get everyone included. And if any of you have ideas about advocacy to make sure more people have access, especially more older individuals, I'm very happy to work on that. As we go through, and most of these graphs are set up in the same way, so let me orient you to these. So this is mostly, as I said, a condition in terms of development and behavior, and this is taking many of those common concerns, and this is the number of individuals first, and then just calculating that as a percentage. So in this particular case, for instance, for individuals with intellectual disability or developmental delay, 27 out of 28 of those individuals, or 96%, have that as a feature. And that's not surprising, I don't think, in terms of a common thing that we see in our children. Within this, or as well compared with this, is language delay. And I would argue that these two are close to 100% in terms of what we're saying. People may think about it slightly differently, but when I have a chance to meet individuals, I find that this is pretty much close to 100%. Now, importantly, the good news is these are the two main things we're seeing. We're not seeing nearly as much about other associated features, but Remember what I told you about the age, right? These are still young people. And in terms of how things might change over the life course, it's not a guarantee that at some older age, one of these individuals might have some different issues than what they're having now. But here's what we're seeing. About a third of our community has autism. And so with that, that's helpful to know in terms of being able to access the right services, ABA therapy, other thing that we need in educational services. But it's also important to realize this is only about a third. It's not everyone who has autism. And it's interesting to understand why or why not. But at this point, we don't know why that is. But people have different manifestations. We also see that there's some other issues with anxiety and problems with attention, but again, and these are small numbers, but again, this could change. And then OCD just stands for obsessive compulsive disorder. So feeling this sort of need to do the same thing over and over again. So that's what we're seeing. But again, main features here, I think what everyone knows about. So reassuring that that's really what you've been seeing and not lots of other things. In terms of neurological issues, we've separated this out in part because this is what neurologists think about. The most common thing, which again, I don't think is surprising at all, is low muscle tone. So this is both in terms of truncal tone as well as arms and legs. And it's why we use things like physical therapy, right? To be able to help in terms of tone as well as coordination and motor movement. So these are things that help in terms of hopping, skipping, and jumping, but also when it comes to fine motor skills. So being able to use your fingers and your hands in terms of writing or manipulating things, brushing your teeth, any of those types of activities. But low muscle tone, very, very frequent. Coordination problems, as I was talking about, or movement disorders, these somewhat related. Also not everyone, but we commonly see this. And although it's not nearly as common as low muscle tone, high muscle tone or tightness or hypertonia, also an issue. Physical therapy, again, helping with both of these, and important to stay loose and limber. For anyone who's having kiddos with high muscle tone, important to stay loose and limber, because otherwise that tightness can lead to problems with mobility, problems with pain, and sometimes orthopedic problems later on. So again, important to continue that physical therapy. For the most part, those are the main issues. We are seeing some slight differences in terms of head size. This isn't concerning. We're not having problems with anyone's head exploding, hydrocephalus, or any of those types of things. Just we see that some people, when you put a tape measure around their head, have slightly different measurements. And then a few people with tick problems. So they may have a little twitching in their face or something else in terms of a movement. Seizures. Seizures, though, are important for us. And I have to admit that in terms of how people have been reporting seizures to us, I think we need to do a better job of this. So with seizures, it's a fraction. It's certainly not 100% of our community that's having seizures. But the reason I mentioned that I'm not convinced we're collecting this quite accurately is we have two different instruments that we use to collect the seizures, and we're seeing sort of different responses or different percentages depending on how we're asking the question. So we're actively working on making sure that we get this number right. The bottom line, though, is either way that we ask the questions, it is still less than 50% of individuals with seizures. So it's not everyone that's having seizures. And when we're looking, as I often do, to try and understand when seizures are happening, one of the issues that I want to make you aware of is that onset of seizures, in other words, the first time someone is having a seizure, is going through quite a wide age range. So we're seeing some individuals who are little itty bitty infants, 5 months of age, when they're having their first seizure, but we're having other individuals who are having their first seizure into adulthood. So one of the things that I'm trying to think as a doctor, as I'm going through this to advise you guys is there any time when we can say, oh, we're past that, we don't have to worry about seizures anymore? I don't yet know what that age is, right? I don't feel like we've got a good enough definition across enough people that we can say, we passed it in the past 18, we're never going to have to worry about this, or past 10, we're never going to have to worry about this. So to me, this is a high priority question because the seizures can be treated and we don't want to miss the seizures, and we have to know if we need to treat, what we need to treat with, and we need to not over treat, because sometimes with seizures, people can get overly treated and then be very groggy, sedated, which impacts in terms of their learning. So with this, the good news, as I said, is that seizures can be treated. And as we've looked at individuals with treatment or individuals who've had seizures, they have needed to continue their treatment. They've needed to continue medicine to keep the seizures under control, to prevent additional seizures from happening. But many individuals are treated effectively with those medications. So again, good news is if we need to treat, we can treat. There are good medications for treating, but we need to recognize those individuals who need to have that treatment. Okay, that's one big point. So hopefully we'll remember that one. Another point that I want to reassure you about, because these percentages, if you look at them, are small, is I look sort of head to toe to see if anyone's got other issues going on. A very small number of individuals with relatively minor types of heart issues. So this is not having a heart attack. These are structural issues that you're born with in the heart. And if your heart is normal and anyone did a sonogram or echocardiogram of the heart, if it's not there, it's not going to pop up there, right? It doesn't start once you're later, you're born with it or not. And again, these are relatively minor things that oftentimes don't need surgery, don't need surveillance. So I want to reassure you, there aren't major heart issues that we're talking about. There are some issues in terms of growth. And one of the things I would love for us to have as a community is what I call a growth chart. So, you know, from your going to your pediatrician, they check the height, they check the weight, they plot it on that little chart. What we're seeing here is that within our community of Med13l, oftentimes our kids are less than the 50th percentile. They tend to be on the shorter side. And for some people, that raises alarm bells. Like the pediatrician gets worried. Oh my goodness, they're not eating enough. Do we need to think about seeing an endocrinologist? Do we need to think about growth hormone? I mean, all sorts of things go on. Whereas if we know that, oh yeah, well, this is just average height for someone with Med13l, people will kind of relax and not worry about this so much. And in terms of treatment, you won't be sort of turned upside down in terms of either undergoing tests you don't need to, or going on special diets or things like that. And so that's one of my fantasies, is that we get to that point, because otherwise we're seeing folks that are having problems in terms of growing, and the problems tend to be more severe the younger the children are, just in terms of being able to get feeding coordinated and sort of getting on the right track. Relatively infrequently, but hypothyroidism was one other thing we see, or low thyroid function. Vision. So vision, you're seeing, again, it's still not everyone, thankfully, but you're seeing a lot of different vision issues. And the reason I bring this up or point this out is because these are all treatable issues. So everything that I put up here is something that an eye doctor can treat, either with glasses or with surgery or patching, but there are ways to treat this, and they're incredibly important, because if you can't see the world clearly, you can't navigate the world, you can't interact with the world, you can't learn effectively. And so this is kind of the first thing. Vision, hearing, two important senses in terms of being able to take in the world around you. So with this, there are many different things, but some of the things we're seeing are either being nearsighted or farsighted, problems with astigmatism or cross eyes. So whenever you're seeing this, if you're seeing that, you know, you're just sort of walking around and you're seeing that your child just doesn't feel like they're navigating as if they know where they're going and can see where they're going, time to go in and see the eye doctor again and get things checked up and make sure the prescription hasn't changed, because the prescription can change over time, just like at least mine has changed many times over my life course. Again, in terms of who to see, you need to see a pediatric ophthalmologist, and ideally someone who deals with children with special needs, because it's sometimes hard to examine, sometimes hard to examine our kiddos and to get an accurate measurement and figure out what they need in terms of that. But do keep this, especially for those of you that are home or new to a diagnosis, keep this in mind. Okay, so one other thing I didn't have on the other slides, most of these are things that I've covered before, but gastrointestinal issues are something that we also see, a combination of diarrhea, constipation, sometimes both, even within the same day. But so those problems we talked about in terms of low muscle tone with the muscles on the arms and legs, also low muscle tone in terms of the intestinal tract. And so things can slow down, that can lead to the constipation, problems with the sphincters that keep things down in the tummy, can lead to things coming back up and bad heartburn. And sometimes the kids can't even tell us why they're not feeling well. They just aren't having a great day, but sometimes it's because of some of those intestinal issues that we're seeing. The types of treatments that work for this are a little bit of trial and error, a little bit of his diet, and some of you guys have figured it out in terms of sometimes it's a lactose-free diet, sometimes it's a gluten-free diet, sometimes it's something that helps move things along. It's a little bit of trial and error, I admit. And then sometimes it's things for constipation, either that need a clean out or something to help things flow, and movement helps as well. So keeping active also helps keeping things moving along. The other thing I mentioned a little bit, it's gastrostomy tubes are not very common, but sometimes our little ones, when they're just getting sort of started in terms of that failure to thrive or not gaining weight, difficulty coordinating, being able to suck and swallow. We did have a fair number of individuals who needed a tummy tube, a tube going into their belly to help them for the eating. But otherwise, things have been relatively sort of quiet. I will point out a couple issues. Scoliosis or curvature of the spine is something we often see in adolescence. So as children are going through their growth spurt, sometimes they can outpace that in terms of their muscle tone. Their muscles in their back don't keep the spine straight and steady. And so because, as I said, most of our kiddos are not yet in adolescence, this is one of those things we need to watch carefully. I will not be surprised if the prevalence or the frequency of scoliosis goes up as our kiddos get older. Okay. This slide we put together in terms of medication use because it's a signal to me about how serious the condition is. If it's serious enough to need medication, it's something that you guys are taking seriously. And I put in a couple things that I alluded to earlier. So sleep, 22% of our community is using something for sleep. And that to me is not just like one night where you have a bad night's sleep, like this is a consistent thing. My guess is this number may even go up a little bit higher as some of our kiddos are getting older. But keep an eye on the sleep problem because, like I said, a good night's sleep is sort of helps with a lot of other things. And this is something that I anticipate in Simon Searchlight. We're probably going to go deeper on in terms of understanding better what's regulating sleep and what we can do in terms of helping sleep. I talked a little bit already about anti-epileptic medications, and then some of these other medications, but let me highlight here some medication either for antidepressants or some of the outburst or severe behaviors. And again, I anticipate that as some of our folks get a little bit older, we may see increased frequency of this. Let's wait and see, but at least compared with other conditions, that's sometimes what happens. Okay, so let me switch gears for a second and go to how the children are developing. And this is a measure that we've been using to look at how things change over time. And let me try and orient you again to how this series of graphs is set up. So with this is age, so age in years, age at which a parent filled out this survey. This is a score that goes up here on the y-axis, and each of these dots is a different person, and each of these is a single time point for that person. This line that we've drawn here is just mathematically looking at what the average of the group is over time, right? So this is artificial, but it shows that if everyone were exactly the same, this is what this group would look like on average. But you can see here that not everyone is the same, right? And I think I actually misspoke. This is age in years here, and this is in terms of an age equivalent. So in other words, if you were 4 years old in chronological age, if you were acting as if you were 4 years old, this is what this looks like. And so for normal individuals, they would look exactly the same. Like I said, if you're chronologically 4, you would act like you're 4, and this would be a nice linear with this kind of slope, this kind of curve. On the other hand, what you'll see is our folks are actually pivoted a little bit, right? So instead of developing with the normal trajectory, they're developing positively, but more slowly. And so that's what you can see in terms of this, but importantly, they continue to develop. We expect, and we will be continuing this every year to understand how individuals are developing. So the same person year after year after year, so we can have that natural history that Nick talked about and understand how that unfolds and be able to see over time if one person follows this trajectory. Or the one thing that I'm looking for is some people might follow this trajectory, but maybe someone else follows this trajectory. And how can we figure out what someone following this trajectory is doing? And can we learn anything from that so people that are like this can now bend the curve and look more like this in terms of what we're doing? Or if we find that we have a treatment that we're trying and someone, we know their baseline is like this, we can see what happens over time with the treatment because we can bend that up and see if that curve comes up. So incredibly important. And this is something in terms of the FDA, for those who are thinking about it, really like the Vineland. This is one of those measures that they've really said, we understand this, it's a validated good measure. And so that's part of the reason why we've chosen this in particular. For each of these curves I'm going to show you, we've tried to include in this something that was very understandable in terms of what individuals might be doing. So this dashed line here represents being able to use single words. And so in terms of what you can see in your child and what others are doing, important in terms of language acquisition. So good news is folks going up. Now, sometimes people are asking about, do things always go up? And I would say in general, yes, but there can be certain times when things might stall. So sometimes when our kiddos get sick, sometimes we see them stall a little bit, even sometimes maybe not if a particular development milestone isn't really solid, sometimes they'll lose it for a period of time and then usually gain it back. But that's one of the reasons we try and keep our kids as healthy as we can so they don't have those back and forth. In terms of other, and these are just broken out by the other domains on the Vineland. So based on 13 individuals and looking at personal care skills, again, it's just another set of behaviors or another set of functionalities. What you can see is folks are gaining those skills over time, ability to be able to feed themselves. Many individuals achieving those milestones by about kindergarten, being able to dress themselves, fewer people reaching those milestones. And again, we've got a big gap here in terms of all those teenage years, but certain individuals by the time they're reaching adulthood, able to do some of those and have greater independence. When we think about social development, so being able to interact with others in a meaningful way, our slope is a little bit shallower here in terms of what they're able to achieve. And this is hard, right? If you're not able to communicate with lots of other people effectively, if it takes a special way of doing that, it's harder to interact with others. And so with this, the good news is folks are gaining skills in terms of being able to make eye contact, some of those social interactions, but being able to show interest in friends is harder to be able to do. And so hopefully with being able to get more of those foundational skills, we can then achieve some of these. In terms of gross motor skills, this is also an area that's been a bit challenging. And so with this, we're not seeing decline, but we're not seeing as much of that sort of upward slope. And so being able to walk and ambulation for independence, really, really good that we're achieving that. In terms of some more complex things, a little bit harder. And I have to admit, I think what I care most about is safety. So if able, folks are stable on their feet and ambulating, that's one of the things that's most important to me. Okay, I'm in the final stretch here. So now looking at some of the things that we see with behaviors, I'm going to break these out. This is something, by the way, that we use a standardized instrument called the Child Behavior Checklist. And this is broken out by 2 age groups, which is part of this instrument. So the lower age group, those less than 5 years of age, 22 individuals responding to this particular instrument, then the news here is good. So when we look at this and score it, these are all the different areas where there could be behavioral issues. So aggression, sadness, anxiety, attention problems, oppositional behavior. And this is over here. If one of these bars were to be way over here in the significant concern, then that's when I would be concerned. And the good news is we don't see any of these either in the significant concern area or in the mild concern area. But again, remember, this is young children who we're talking about. But this is the good news. Now, this is the same thing plotted out, but now plotted out in 17 individuals who are older. So ages 6 to 18, same categories we talked about before. And then again, we're not seeing for any of these significant concern or mild concern, but do remember that most of these individuals, even though it's the older group, most of these individuals are still single digits in terms of ages. And I do think in terms of when we see behaviors change, puberty is a time of big change for all children. And so I'd say we're still watching this in terms of hoping that this stays exactly the way it is, but it's a gap that we need to fill in terms of understanding those issues. So overall, some of the issues that we see, and I know this resonates with many of you, is that in terms of just being able to sort of function in daily life, sometimes it feels like a short attention span, difficulty in terms of needing what they need when they need it, and being able to do this sometimes leads to some impatience. New things are hard, and anxiety comes with those new things. And I know you guys have figured this out, but in terms of just having predictability and being able to convey that helpful in terms of day-to-day life. And for the slightly older individuals, the one thing that I wanted to just emphasize here as we think about health in the long term is potential that we need to watch here in terms of just eating behavior. So in other words, how you eat, when you eat, how much you eat, what types of food you're eating. And the reason I say this in particular is that when I look at older individuals in our community, if there's issues in terms of weight, we tend to have more issues with diabetes, and some of the medications we ultimately have to use can sometimes lead to problems with weight gain. So it ends up being a more complicated problem than it needs to be. But if we can be careful about nutritionally our folks when they're young, it ends up helping us. So combination of healthy food, physical activity, being mindful of this. I'm not saying, put anyone on a strict diet, but just being mindful of this so that we can make sure this doesn't become a problem later. So in summary, as we're putting all of these things together, I think it's the good thing is not really surprises. So I don't think we have, again, what you didn't see. You didn't see things about cancer. You didn't see things about diabetes. You didn't see things that you might have been worried about in the background. The numbers are still modest in some cases. So I think we need to be more certain of this. And when we do see some of these issues, either with vision or seizure issues, they are treatable. That's the good news. We just need to make sure that we diagnose them and then get them to the right people to help. Okay, so with that, I'll be glad to stop and take questions. And I think I'm going to take my questions now and then bop out, but I'm around, so you can always grab me later if you want to talk about something privately.
If anyone has any questions for Dr. Chung, if you wouldn't mind coming up to the center microphone and or raise your hand and I'll be happy to give you the microphone.
Just, there's a mic right up here. We're doing this for the folks at home so they can hear it too.
Okay.
Yeah.
Hi, everybody. So I have two comments. One is that I'm really happy that you talked about the vision aspect of it. My question is about vision processing because that involves neurology. And I'd like to extend out to the parents because my daughter has a TBI. She is part of the Bureau of Blindness and Low Vision. She's getting services through them and orientation and mobility. So that's something that I didn't hear you talk about vision processing piece of it, but there is something with eye tracking and pursuits and saccades as well. And some other optic nerve things. So then we're looking at potential like depth perception, peripheral field loss and things like that. The second,
I'm
go ahead,
very
sorry.
short attention span. Let me do this one before I forget. So for those of you that maybe it went kind of fast, so cortical visual impairment is also an issue. So it's not just structurally the eyes, but it's the part of the brain that's receiving the signal from the eyes and being able to process that information and do it accurately in terms of that. So you're right as well. In terms, the reason I focused on the eye portion of this specifically is that is more amenable to the treatments that we have available. I'm not saying that CVI or cortical visual impairment, that there's nothing that can be done, but it's a sort of longer, harder road in terms of doing that, but you're absolutely right. And if you need vision services, there are lots of vision services available either for the here or for the here part.
right. And the second one is, have you seen evidence of like talpus equinus or clubfoot?
What
in
was
these
the
chil-
first blindness?
I think it's called talpus equinus. Is that correct? Or the term is clubfoot?
Oh, I'm sorry.
Yeah,
So
it's the mask.
yeah. So there are a small number of onesies basically that I'll describe. So for anyone who's really interested, I'm glad to talk to you offline. So there are a small number of congenital anomalies. So things that people are born with that we don't see very frequently with Med13l, but I anticipate once the numbers come up, if you aggregate them together, they're going to be more common than they are in the general population. And I think Med13l is probably a part of the answer. I'm not sure whether it's going to be all the answers. So one of the things you mentioned was clubfoot is the sort of the way that we oftentimes refer to that. We've also seen congenital diaphragmatic hernia. We've seen some other, the congenital heart disease that I mentioned, I think is part of it. The good thing is that the majority of people don't have any congenital anomalies, but I think in the aggregate when you, and we're not seeing that everyone has the same anomaly when they're born with, but we're seeing if you put them all together, more than we would see in the general population. So I think it's part of the answer, but I suspect there's something else as well in those individuals.
Right. Okay. Thank you.
Yep, sure. Great question.
Thanks for being here. So when it comes to getting our numbers up to get more data, what is Simmons Searchlight? What kind of outreach and accountability do we have to get those numbers up on your end? Because I want to be part of the solution to get our
Yeah.
numbers up. So
Yeah, so I think probably the easiest thing to do is offline. Let's have a meeting, Jennifer Chernagel, who can wave her hands here, and we're happy to help, meet with you here or once everyone gets back home. In terms of a campaign, so to speak, to get the word out, whatever distribution channel you guys are using in terms of Facebook or eBlast or whatever you're doing, I think is the start to that. And then if we need to meet you by saying, email this person directly if you've got questions, if you're stuck, whatever it is. We've done other things where we've done like an online thing, in terms, and I'm happy to personally do that if this video doesn't work, but being able to online talk to your community, answer questions, ask me anything, if the question is it people that just are too busy? Is it people that are scared to do this or people that it's a technical challenge? And they're kind of different answers to those different portions of it. But if people want to participate, then we will meet them where they need to, where we can.
So you mentioned diet as being important for preventing bigger issues down the road. With any child, typically developing or otherwise, it's hard to get kids to eat their vegetables, not eat too much dessert, all these kinds of things. And, in our case, our daughter loves simple carbs. She loves pasta and bread and so forth. And it can be tough to get a good diet. So I guess, could you expand a little bit on techniques, frameworks, what a good diet looks like? I mean, how we really try to instill those things now?
Trust me, it's a complicated question. I started my entire career thinking about this, and right now, it's a problem not just for our community, but for the entire country and the entire world, right? So it's not a simple issue. So one of the issues to be mindful of, because we try and do incentives for kiddos in terms of behaviors, but just be mindful in terms of how you use food as an incentive. So keep that in mind as just a simple thing. And so as an example, I'd much rather use stickers than an ice cream bar, right? And so some things like that. Another thing that's really hard, and I admit it's really hard, is that if you have food in your pantry and your refrigerator, right, everyone in your household, it's easy enough to grab snacks that are not the most healthy snacks. And so it's hard because the whole family is going in, right? It's not just one person in the family, like the whole family has to agree and get down with this. Now, on the other hand, it's a good thing for the whole family, right? So you have to think of it in that way in terms of doing it. And you shouldn't deprive anyone, right? So it's not a matter of like, you're now like no carbs, you can never have birthday cake, you can never have dessert, right? That's just the wrong way of going, because then people tend to swing the other way. So it's things in moderation, right? In terms of all of that. And, there are things that are easy things to get rid of. So I call them empty calories in terms of beverages. If there are things that are empty calories, that's an easy place to cut where people, you don't mind it so much. It's not so painful. And if you're doing it, do it a bit at a time. It's not like, just complete, overnight, this is going to happen. But I bring this up, like I said, because some of our young people, if they have this problem and continue that problem into adulthood, it's harder to turn that clock back. Sort of when your body sets that, what it thinks is its thermostat for weight, it's hard to reset that thermostat.
Thank you. And then a related question is, there's a long history of the ketogenic diet being used to prevent seizures, even though it seems that only a minority of our population present with seizures. A majority, at least, seem to show irregular EEGs. And so, I guess the question is, could a low carb or ketogenic diet be a positive for our population at large?
So I've wondered that, not for Med13l, but I've wondered it for some other conditions. So just a couple points. I do think the EEG is incredibly important. And so for those of you who have done your EEG with the team here, I think that's really important to do, because I think we're trying to figure out, will that be something that'll help us in terms of better understanding who's thinking clearly, cognition, outpoints for clinical trials, all these things, regardless of if you're having a seizure or not. So that's number one. A true ketogenic diet is tough, and like true ketogenic diet. And so I'm not going to tell you guys all to go on a ketogenic, put your children on a ketogenic diet, because there are kidney issues that go with that. It's a very complicated thing. Just going on an Atkins-like diet, so in other words, where you're eating steak all the time, isn't necessarily going to do it either. So I think the jury's still out in terms of this. I think it's something I'd be very curious in terms of starting with people who may have epilepsy and doing that and see how much that helps in gathering some data. Very quantitative EEG to do that. and then we can ease into seeing whether or not that'll help other folks. But it's a great observation and a good question to be asking.
Yesterday, you mentioned that you're working on equipment that you could take home for a sleep study or maybe an EEG, and I would love to hear more of that. Separately but connected, my son doesn't have full-blown seizures, but has seizure-like activities, and they want us to track when he has those, and we can't tell. Like when he's staring off into space, does he really like this movie, or is he thinking of something, or is that a seizure? And I wonder if the same take-home equipment / EEG could also help with recognizing seizure events.
Yep, great question. So we're at this point exploring at the Simons Foundation several different gadgets. We funded investigators specifically to be able to look with sleep, especially as you may have seen from what I was saying. We're especially interested in sleep and gadgets to be able to do that in your home environment, not too tech heavy in terms of being able to do that. And some of that equipment may also help us in terms of EEGs. And then there's some other things where you don't have a full cap for those of you who have done it. It's not the full cap with all of the leads, but maybe a small number, 2 or 4 leads to be able to get information. Because I agree with you, just by looking at some children, I can't tell what's going on with their brain waves inside. I don't know yet in terms of as we roll out which communities we're going to roll out to or which locations we're going to roll out to. I'd suspect it's going to be in the United States rather than abroad initially. Part of this is we're waiting to see what communities it might be most beneficial for. It is likely, though, that as we're doing this, we would probably do a few, like a gene as a group rather than just one person from a gene group, if you know what I mean. So part of what we're looking to do is see how many people do we have in specific gene groups? How many people do we have that in that gene group look like that might be necessary, and how much are you guys interested in that? If you tell us, you can leave us alone, we're not going to torture you with that. So if you want to be one of those people that are volunteering, if Med13l says like, we're all in this, we want to volunteer, we want to move this forward, we'll learn from you guys in terms of feasibility. Can we do it? Does it work? Does it help? And then the reason you see these other groups here is that we'll then take it from one group and apply it to more groups after that. So I'm counting you as someone who's volunteering when we get to that point. And if that's true for the larger Med13l community, that'd be fantastic.
Thank you very much, and I do look forward to hearing more about that. Completely unrelated, my son was born with a cleft palate and a hair lip, and we were led to believe that was very common, and we didn't see it mentioned. Could you talk to the prevalence here, please?
Yes, so we have one in the series that I talked about. We have one person represented with a oral facial cleft. As I was alluding to, we have several, not several, we have a few onesies. So like I said, the club foot, the congenital diaphragmatic hernia, the cleft, and I'm not trying to out anyone. I don't know if it was your son exactly who was represented, but those are all just single individuals with that. Now, theoretically, that could be by chance alone, right? It could just be a random thing. But I think my hint is that that's not going to be random, but that there's probably some reason why some people have a club foot, someone else has a cleft, and someone else has nothing in Med13l. There's probably complicated.
I just want to follow up on all the seizure questions, because I think we were probably the family who messed up your data, because we're on seizure medications, but we don't have seizures, we have ESES. So like, I know that was sort of in the questions. And I guess I'd love to hear more about that diagnosis in kids with neurodevelopmental disorders, because we went through quite a journey with sort of some neurologists sort of saying, oh, this is a very abnormal EEG, but this is just part of having a neurodevelopmental disorder, with other neurologists or epilepsy specialists saying like, no, this is clearly ESES and it needs to be medicated immediately. So I don't know if other families have sort of had that divide or how that's come out.
Okay, so I'm gonna try and Leanne, you can just shout out. I'm seeing we have 4 individuals with SES. Dr. Green Schneider is in real time looking at our data set. So that's. So you're not alone is the point. I think this probably is part of Med13l. And I think, and for anyone who wants to, there are several, or at least 2 child neurologists who are here at the meetings, and feel free to grab any of them to ask as well. There is a debate within the community in terms of what to treat and when to treat in terms of that. And just for full disclosure, I'm not a child neurologist. And so I don't think there's consensus in terms of that. So if you were hearing that sort of lack of disagreement, I don't think it was just your experience. I think they would say the same. Now, the question I would have back for them is when we get to Med13l as a group for this one very specific community of neurodevelopmental disorders, what should the answer be? And I would hope that we get greater specificity and recommendations towards standards of care that'll be specifically for this community. And that's what I'm hoping for our next game. Like I said, growth charts, standards of care, clinical care guidelines. I think that's if we can get our numbers up just a little bit more, that's what we can look forward to. Okay.
Information being included in this presentation.
And the data freeze was about 6 weeks ago, 8 weeks ago. Something about like that. Okay, so I'm going to say this out loud to make sure I heard it right and so the folks at home can hear. So what I heard is that as we're thinking about growth charts or things like that, being able to have this with and without autism in terms of developmental growth charts, was that the question? So we have even greater specificity within Med13l as an example. And if we can get the numbers up, I think that's possible, right? The big thing is being able to get the numbers. And you had mentioned Down syndrome. So just as an example, this comes from the playbook, if you will, of other rare conditions. So Down syndrome, other things have their own clinical care guidelines, and that obviously is more frequent. And so they've been able to develop that. And we in part are just hopefully now with the greater recognition and testing, we'll be able to identify more of our folks and be able to aggregate those data. But that's exactly the point, is to try and do that with as much specificity as we can. Okay.
Thank you so much. Okay, next we're going to hear from Chad Grueter.
Right. So while they're bringing up the slides, I'm a PhD, basic scientist. So what I'm going to talk to you about, or what I'm passionate about, is learning everything I can about how Med13l functions, what it does. And I can tell you, we're a long ways from knowing the answer to that. But with the use of the tools that you're going to be hearing about from me, from Dr. Strich here in a little bit, we can learn a lot, and we can learn a lot quick. So I want to point out, if you have any questions, you can interrupt me as I go. If you want to wait till afterwards, that's fine. But for some of you, might be more comfortable just emailing me. I'm super excited about talking about what I know about Med13l, what I know about how it works in the complex. And if like I said, if you have any questions, I'm happy to answer them either in person, or I've met with a couple of people over Zoom. I'm really excited about doing that. So with that in mind, again, I'm a basic scientist, so I want to know how Med13l functions. So we're going to, for this talk today, we're going to look at it in the not only the context of just Med13l, but it's like everything else. It plays on a team. So it functions with these other proteins and other genes, and we'll talk about those as well. So first, we want to talk about, basically what is Med13l, how does it work? That's another important question, and we don't know all the answers yet, but we're gaining on understanding that. And then the middle portion of what I'm going to talk about are the Med13l mouse models that we currently have, and then just briefly mention the ones that are being developed. And lastly, I thought I would give a couple examples of small molecules that I've worked on in the past that target components of the kinase submodule not specifically Med13l, just as examples of what we can learn from this. And I do want to point out that my training is in cardiovascular disease, so I'm new to the above the shoulders work, as I've heard today. So when we think about what Med13l does, or when we think about biology in general, there's this general dogma that we have to consider, and that's that hopefully most of you know that DNA is translated to RNA and into protein, and this is well, it's a fact. What we're looking at, so the DNA, there's about 3 billion base pairs of DNA that encode your genome, and within that 3 billion base pairs, there's only about 22,000 genes, which that only takes up about 3% of your actual genome. And one of the questions that I always want to know is what happens with the other 97% of the genome, and a lot of that is functioning as regulatory components as well. And what those regulatory components are for the expression of, for example, of these 22,000 genes. So these 22,000 genes are not always expressed at all times. So for example, in your eyes, you have rods and cones. They're not expressed in your liver. You don't need them there, so they're not expressed there. What we're trying to figure out, what Med13l does, is it participates in this process of transcription, and that's the conversion of DNA to RNA. And it's part of this larger protein complex called mediator. And what mediator does is it basically, and this is an extremely schematized cartoon of what it's doing. It's this large complex, and what it's doing is it's taking the information coming in from the cell environment and converting that to information that this machine here, RNA-Pol2, can then use to make, it's the transcriptase that creates, or that makes the mRNA, or copies the DNA to RNA. The mediator, sits here in the middle, well, at least in the middle of my world. I did it again. And it's a very large complex. There's about 30 to 31 proteins in the human mediator complex. And it is a highly dynamic complex. There's a Nobel Prize awarded to a snapshot of the structure of this to Roger Kornberg. But we still don't know a lot about how it functions. But what we can do as a biologist, we are taking a reductionist approach. So we look at things from an individual standpoint. So what I'm going to do today, if I can't stop doing that, is look at the part of the mediator complex. So there's this, and it's not drawn to scale by any means. There's the core complex that's very large, and it's necessary for transcription of basal genes. There's also this kinase submodule, and that's where Med13l resides. So kinase submodule is super exciting to me because it regulates this process. It's a key regulatory point. So in my mind, even before this, I became involved with the Med13l Foundation, it's a potentially targetable submodule. So like I said, these proteins work as a team. So Med13 and Med13l are what we call paralogs. So back in evolution, about when vertebrates were evolving, Med13 duplicated. So we have two versions of it. Those two versions aren't equal, but they're highly redundant in a lot of ways. They do have individual functions. So, and I think if you guys were looking on Simon Searchlight, Med13 is also listed as one of the genes on Simon Searchlight. So what I'll talk about today is the combination of the data I'll talk about as Med13 and Med13l, because I've been studying it a lot longer. There's also Med12, Med12l, cyclin C, CDK8, and CDK19. You'll notice that 3 of the 4 have homologs. So both CDK8 and 19, for example. They all function in a 1-to-1-to-1-to-1 ratio. So there's stoichiometric. Whenever Med13 is present in this subcomplex, Med13l is not, for example, and vice versa. But they can form, as far as we know, they can form different combinations. So it's a highly dynamic subcomplex as well. So when I look at it, I want to know what it's actually doing. So I like to think of it with different analogies. And I think in the kinase submodule, one analogy that it's not a perfect analogy, but one that I like to use is that of an airport. And if you think of, the polymerase is maybe the airplane, the mediator complex is it functions to regulate the communications process. So it's the core to interpret, the information coming in, whether it's people booking flights or people, missing flights, et cetera. But what the kinase module to me does, or one way I like to describe it, is it works kind of like the communication tower. So you can imagine, on a normal day without thunderstorms, air traffic is flowing normally. Flights are coming in and coming out. You don't necessarily have to have that much information coming from the tower. It's there in case, in this particular analogy of emergencies or just normal function. So that's the way I see the kinase submodule working. So under normal conditions in the cell, it's necessary, it's there, but it's not playing a huge role under what we call baseline conditions. It's when things happen that it actually is necessary or kicks in to action. So like when the thunderstorms disrupted like 1,000 different flights and people had to rebook their flights and you have extra airplanes coming in and out of the airport, then this tower is extremely important, right? To coordinate everybody, all the planes landing and taking off. Well, the same I think is true about the kinase submodule as a whole. So when the cell is differentiating from a stem cell to a neuron, going through that differentiation stage, that's when these protein complexes seem to be more important. Or in a state of a cell, like I study cardiovascular disease, in a normal heart, the kinase submodule is there, but we don't really see any major phenotypes until we stress the heart. So under those stress conditions, so we give the mouse a heart attack, or we give, whatever treatment it is, then we start to see the need for this kinase submodule. So it does have, it's important under basal conditions, but its major role is in those transition states. So with that in mind, so that's the kinase submodule as a whole, thinking about it. And I do like to think of it as a whole, and Med13, Med13l are different components of that team. So Med13l itself is about, I believe it's 31 exons. It's a very large protein. It's about 250 kilodaltons. To put that in perspective, about an average protein is about 50 kilodaltons. So this is a huge protein. Med12 is also quite large. It's, as far as I know, it's ubiquitously expressed in all eukaryotic, in all mammalian cells. And it's, what I've seen at least, is its expression levels are primarily regulated at the protein level, meaning it's degraded more so than the RNA level, but that doesn't mean it can't be regulated at the RNA level. It functions as a scaffolding protein. What that means is it basically links up proteins to each other. So it integrates those signals coming in, and it brings the kinase submodule, for example, in close proximity to the core mediator complex. So it doesn't have any enzymatic activity, I guess is the word I want to use. And then its overall function is to integrate these signals when you have the main thing is when there's change in the cell environment. And this changes the transcriptional program, because this is all about, at least, and Randy's, Dr. Strich's going to tell you another story, but at least Med13l in the nucleus is all about regulating transcription, as far as we know. That changes the function or the health of the cell. So the next question is, why do we want to study mouse models? I mean, the ultimate goal is to treat the human syndrome. Well, the idea is that we need to develop tools in order to model the human syndrome, where we can actually manipulate the tool, in this case, the mouse, so we can learn a lot faster. Mouse life cycle is a lot shorter, and we can control the conditions. So again, biologists are reductionists. We like to keep things as simple as possible in order to be able to interpret the results. So we want to see what phenotypes, if any, that the mouse might have that recapitulated in the, or vice versa, the mouse recapitulates the human phenotype. So we're looking for changes in the mouse that we can use as a readout as well. So as a biologist and just somebody who gets really excited about, the molecular aspects, we also can use these, the mouse model to identify the physiological, cellular, and molecular changes that occur in the different Med13l mutations, whether it's a loss of function or single point mutations or whatever the mutation might be. So we can use this as a tool to better understand that. And then what I think is really one of the critical things that you'll learn more about today, or as we go along, is we can use these models then to test small molecule therapeutics. So without, they basically provide a preclinical model for the therapeutic approach. And it's extremely complementary to the cell culture work and other studies that are currently ongoing. And then, of course, there's the developing the genetic rescue approaches as well. We need mouse models to prove the safety and efficacy before taking it in combination with the cell culture work. So I spent the last 10 years, so I started studying Med13l, or Med13 actually. I've only been studying Med13l for about 2 years. So I spent the last 10 years of my life collecting tools to study this kinase submodule. So in that time, we developed, or I've collected or made a bunch of different mutant mice, and they're not all listed here, but most of them are. So we have Med13 and Med13l conditional knockout mice, and I'll describe what that means in a little bit. We've got Med13 cardiac. So I started off, I'm a cardiac biologist. So we have cardiac overexpression of Med13. We have CDK8 knockouts and CDK8 overexpression. So knockout is where you lose the protein, overexpression is where you increase. We've got CDK19 knockouts, those are the newest in the lab, and then cyclin C as well. The one missing is the Med12, and a colleague of mine, a very close colleague, is studying those, Med12 and Med12-like. The one thing I did not mention, and this is an opinion from a basic scientist, is the phenotypes that we see, or that I've seen from the human studies, they overlap quite a bit for this kinase submodule. So there's Med13, Med13l, Med12, Med12l, CDK8, and CDK19 have all had mutations that have been identified with, and they seem to me at least, as a non-clinician, to overlap. So there's a lot of, but we can learn a lot by studying the combinations as well, because like I keep reiterating, these proteins are working as a team. So, but what I want to focus on for today, and what you guys are most interested in, is Med13l. I'm going to show you data from both Med13 and Med13l. Again, that's because that's the mouse model I generated a long time ago and been studying the longest. So why can we compare these? Like I said, this was a gene duplication a long time ago in evolution. There's lots of overlap between Med13 and Med13l. I think size-wise, there's about 30 amino acids different size-wise. Oops, you could run by. Med13l is just a little bit longer. What we define as different domains within Med13 and Med13l are conserved between the two. There's slight variations. And what we can learn from these domains, or we can infer from these domains to develop hypotheses to test what these actual portions of the protein are actually doing. So like I mentioned, these are very large genes, very large proteins, and we still don't know what different portions of the protein are doing. And if you look in some of these, I've highlighted some of the different mutations that have been identified. This is by no means all inclusive, but one thing I want to point out is that there's not a hot spot, so to speak. In other genes that I've seen today, that all these mutations would be in one region. This is throughout the entire protein. So we have a lot of work to do in order to figure out really how this protein is working and folding and how it plays well with the rest of its team. So in looking at some of the data, there's two different types of mice, two different types of mouse models that we have. I'm only going to talk about one, but I want to describe the other in more detail, and hopefully in the future be able to give you updates on it. So there's the two basic types of mouse models are conventional, and this is discussing knockouts in this case, mouse models where the gene is knocked out or deleted in every cell in the body in the mouse. And these are valuable because that's recapitulates what we would see in the human population. What we can also do in the mice that I have they're called conditional knockouts. And the conditional knockouts as a biologist allow us again to take that reductionist approach so we can look specifically in space and time. So what cell type or what organ we want to get rid of the gene in. So for example, I'm cardiovascular, so we wanted to delete Med13l in the heart. I've done that, and see how deletion of Med13l only in the heart at a specific time point. So we could either look at embryonic development or we could look in adults and see what happens. And then we can learn a lot more about the protein in the absence of all the other confounding factors like development, for example. So we can skip that developmental stage and compensatory type stages, and we can ask specific questions about what's that protein doing in that cell type at that time. So we have those tools. So right now, I wish I had more data, but what we're doing with the Med13l mouse. So I've got the condition or the conventional knockout. We're breeding the conditional knockouts right now. Like I said, I've already studied to an extent the cardiac knockout. We're also breeding mice with the neuronal deletion, which is obviously more pertinent to this the syndrome. So we can delete Med13l specifically in neurons, and we're doing it in all neurons in our first pass. But later we can go in and if there's a specific brain region that we want to look at and we have the tools available, we will look more specifically for that. We're also looking at what I call a transient progenitor cell population called the neural crest, which I think could potentially play an important role in the etiology of this syndrome as well. So we're still in the process of generating these tools, but we've got some pretty exciting opportunities to study this and really figure out, do we need to treat, anything below the neck, as it put eloquently earlier, or if everything is above the neck, for example. And using these mouse models, we can hopefully start breaking that down so we can have a more directed approach from that perspective. So I am going to show you just a little bit of data. There's mice in these pictures, so if you guys have issues with mice, you might not want to see like actual mice in the next slide or two. But in our mice, we control the environment. We control what mice breed, and so we set up matings with a heterozygous mouse. And if you guys ever did Punnett squares back in genetics, you'll know that the outcome you'd want to see is 1 to 2 to 1 ratio in this. And you can see with Med13, like when we breed two heterozygous mice, we've never got a homozygous null. So this in either Med13l or Med13 like it's Med13l or Med13, meaning that this gene is absolutely essential for early, in this case, this was at birth, for embryonic development. Let me move on. So you need at least one copy, and we know what this is pre-implantation, and there's a little bit of information about when it is necessary. But what this also suggests, whereas I've made the argument that these guys are redundant, in a lot of ways they are, but they're not completely redundant, or these guys would have survived. So there is some unique properties of each individual gene, of these individual genes. So, which I think is an important finding. So we're just beginning to characterize these mice. And one of the things, the simplest thing we could do is look at their growth pattern. And so we've looked at, and we just, again, Med13l was not an original focus. It is now because of you guys, but it was not an original focus. So we took the body weights of mice when they wean them. We wean them at 3 weeks of age. And we found one thing that was obvious was that they're smaller. They're about 15% smaller than their wild type siblings. So, and it was very consistent across multiple litters. When we compare that to the Med13 mice, again, I've studied them a lot longer. In Med13 mice, and I think this will happen, we'll see this as well in the Med13l, they're small. So one of the questions is, do they start off smaller and just, or are they delayed, or they're always smaller, et cetera? Well, in Med13 at least, it appears that even in embryo, this is about be the equivalent of the end of the second, beginning of the third trimester, if you will, in a mouse. That they're smaller even in utero. These guys are a little bit smaller than their wild type siblings. And then over time, this is weeks of age. So a mouse becomes mature at 6 weeks of age. So over time, they do have a growth delay over time. And you can see this 3-week time point matches almost perfect with the 3-week time point and body weight that we see with the Med13l as well. So the next thing we wanted to do is see where Med13l is expressed. And we had a mouse model that we can do that to an extent. It's not very high resolution, but what I had 2 regions of interest. Again, the heart. I wanted to look in the heart and see where Med13l was, and then we wanted to take different pictures of the brain and see where it is. And what you're looking at here, this M stands for male, F is female, plus over plus is a wild type, and then FL over plus, it means it has a what we call a knock-in. It's a flox allele with that we can look at and see. Basically, in this case, we're looking at the blue stain. So anywhere where you see blue, that means that's where Med13l is expressed under normal conditions in a mouse. So you can see, a lot of or the very first paper on Med13l, it's called, at the time it was called ProCyte 240 back in 2004, in Search Research, was identifying transversion of the great arteries. So we wanted to see, if that happened, if it's expressed in adult outflow tract, which is the great arteries here, and it is. It's expressed in the heart as well. It looks like, throughout the entire heart. The next question is, where is it expressed in the brain? So we got 2 different views here. So this is again wild type, and this is the marking where the Med13l is. And this section would be if you took a section basically in this case right about where the eye is and go straight back and look at it from the side. That's what this view of the brain is in the mouse. You can see this giant olfactory bulb sitting up here. And this is the cerebellum right back here, and the hippocampus is right here in the middle. So you can see that it is highly expressed in the brain. We look at a different section. So this would be taking the brain and cutting it like ear to ear and looking at it from straight on. And you can see it's also expressed in different regions of the brain. What's interesting here is, so one thing I want to point out, that like these regions, like the hippocampus, which is right here, there's the order of the neurons are highly structured. So it might be that those are more pronounced. But what we also want to know is there's lots of regions like here in the midbrain that don't have a lot of staining. So we need to find out if Med13l is truly highly expressed in those regions. I would suspect it is, but the staining is just more diffuse. So those are the types of questions that we still have. What brain regions are where it's expressed the most, and where might it be playing the most prominent role? So just because we want to know, at baseline. So in previous studies or other studies of mouse models, they don't often, sometimes you have to hit them a little harder to see a phenotype, meaning that, often you don't see a phenotype in a heterozygous mouse for a specific gene that you would see in a human. Sometimes you need to make the homozygous mutation. So when we originally did these studies, I was actually surprised to see any phenotype in the heterozygote. But since we decided to go ahead and look at, Med13l plays a role in transcription. So I had to look and see if there's any transcriptional changes. So what we did is we decided to look at the hippocampus, and the hippocampus is the most highly studied brain region there is. It basically integrates learning and memory, short-term learning and memory. And there's a lot known about it. So that's the place where we started. We decided to look in adults. So we looked at 6-week-old mice just because they, in theory, would have the least variability. So we would have the developmental changes to think about. And we just wanted to see, are there changes in gene expression in Med13l versus their litter mates. And you can see there are about 300, almost 300 genes that were significantly altered in the hippocampus of these Med13l mice. About the same for the Med13 as well. I did list a few of the top genes just because these genes are I mean, they're transcription factors, so that got me a little excited. I'm not going to get into any detail what each one does, but it was pretty exciting to see. So when we looked at it in more detail, a different pathway analysis and stuff, so we can really dive in and see what pathways are being affected or not affected. What we see are that there's a lot, and without getting into too much detail, there's things like all the tube morphogenesis, some specific pathways, some transcriptional pathways that are misregulated. Med13 seem to give more specific results in more what makes it easier to interpret. So Med13 results showed like long-term potentiation, neuron development, those types of things were significantly downregulated. So this is just a pilot study. It's the beginning of what we want to do and are doing. But you have to start somewhere. So we need to do, of course, a time course and increase the numbers so we can get higher quality data from this. So I do want to make it, so that's all I have for the specific Med13l mice, that the data that we've collected so far. But I did want to make a point that there are mice, and they've been mentioned in the pipeline being made by Jackson Labs, and they cover 3 different categories, basically truncation, point mutation, and a gene deletion that should be pretty exciting to study, and they'll provide a unique look at the function of Med13l. So the reason we want these mouse models and the humanized mouse models, as well as studying the conditional mouse model. So I do want to point out that these mutations for these mouse models will be the conventional. So that'll be in every cell type. So we still, I believe, need to study the conditional deletion in order to figure out what cell types are important and really to break down what Med13l is doing. So the reason we need these mice is to better understand the gene function, what Med13l is doing in a physiological context that we can't learn without having it in the context of the whole body. Hopefully we can use them to screen the therapeutic candidates that are being developed by Rare Base, and then also to test the base editing as a potential gene therapy. So that's really exciting new models to coming down the pipeline. So now I'm going to switch gears a little bit, and this is where I'm going to branch out into the other genes. So I thought, for me, I thought about what I'd want to see if I was sitting in the audience, and I want to see, as much potential as possible. And I will say that I wish I had specific data in the next section on Med13l. I don't, but what I'm going to talk about is 2 different ways to target the kinase submodule itself. And again, I'm a cardiovascular biologist, so this is going to focus on the cardiovascular system a little bit. The first one is an antimer 208A. This antimer, it targets Med13 specifically in the heart. And this is a study. This is the reason. So back in 2008, I began studying Med13 because it was predicted to be a target of this microRNA. And so that's what got me started down this road. And then we stumbled across, this was in my postdoctoral fellowship, this idea that, by manipulating the levels of Med13 in the heart, we can manipulate the whole systemic metabolism. And one way to manipulate the levels of Med13 is genetically. So we can increase or decrease the levels in the heart with the tools we've developed. Another way is through modifying the expression of this other gene. And this other gene basically controls the expression levels of Med13. So this is just obviously a cartoon schematic of the overall finding that by modifying these 2 genes in the heart, we can increase energy metabolism. So we have skinny mice, or we can decrease it and we can generate fat mice. And this all occurs through communication between the heart and adipose tissue. So it increases your basal metabolic rate. So the way we tested this was in the beginning, it was actually by increasing the levels of Med13. So we went from a little bit of Med13 in the heart to about 2 or 3 times the amount of Med13 in the heart. And what we then did because I wanted to study obesity and diabetic cardiomyopathy, I put mice on a high-fat diet. So this high-fat diet the mice go on as your bacon double cheeseburger. It's 60% of the calories are coming from fat. Mice, they love it, they eat it, and they get, as you can see from this guy, they get fat really fast. So technically in a mouse to be obese in black 6 mice, like this guy had about 35 grams. So within 4 weeks, these guys are already obese, and they exhibit the basic phenotypes of obesity. But what I noticed, so my goal as a postdoc was to generate a model of diabetic cardiomyopathy. Well, in order to have a diabetic cardiomyopathy, you need an obese diabetic mouse. Well, as you can see from this is normal chow, this is high fat, these are wild type mice, and these are my transgenic, my mutant mice with high levels of Med13. There's no way this mouse was ever going to develop diabetic cardiomyopathy because it stayed skinny. And this was very novel at the time. We didn't know that the heart communicated to regulate systemic metabolism. And we found that if you look at the red line here, this is the growth or the body weight of these mice on a high fat diet, and compare that to these guys, the wild type. And you can see the wild type, they grow quite easily, quite fast. So that was quite a shock to us at the time. But that's interesting. But this is a genetic model that we forced into play. So now what happens? I told you that we had a way that we can regulate Med13 expression through this other gene. So by giving this drug, and I skipped a step here with the MIR208, we give this drug, we call it anti-208, and that leads to an increase in Med13 levels. So we asked a really simple question: what if we put mice on a high-fat diet and gave them this drug? And what we find is just like the Med13 mouse. So the control mice, these are all siblings, but one with a drug and one with a control. The controls gain weight, they become obese within 4 or 5 weeks, but the mice on the anti-MIR, the anti-208, were resistant to this high-fat diet-induced obesity. And then I spent a lot of time characterizing these, and we had a couple papers on this, one where we sewed the mice together and to make Siamese twins out of mice, and so they share the same circulatory system, and we showed that it is some kind of secreted factor that's leading to this decrease in, or this prevention of high-fat diet-induced obesity. We also find that we can, so this actual drug, the anti-MIR208, was tested in rats by a company. We patented it, and then it was licensed by a company, and it's tested in rats, sheep, and non-human primates, so monkeys. It not only prevents obesity, but it can also reverse obesity. So it's very exciting, and the company has it licensed, and I hope they move on with that. So that was the main takeaway for this group, is that Med13 is a paralog of Med13l. If we can target Med13, we can come up with ideas and ways to target Med13l. So the next one is another study that we've done recently. This one's unpublished in my lab, and this is targeting the kinase. So the kinase part of the kinase submodule. And this is using a small molecule directed towards CDK8 and CDK19. There's actually 2 different ones, CCT251545 and Senexin A. We want to try 2 different, we tried different molecules, small molecules to show that it's not just the molecule, but it's the targeting of the kinase. But, and I won't get into too much detail about this, but again, the study was designed, these are the controls, but what we want to do is a cardiovascular study. We wanted to put the mice on an agent that causes the heart to get bigger and to function less efficiently. So this is angiotensin II. There's a lot of people in the population that have high levels of angiotensin II, and they're on ACE inhibitors, for example. So this is something that happens. So when we do this in mice, it causes their heart to get a little bit bigger, and we can see that. And then it decreases the function over time. So, and we can measure that with an echocardiography or with cardiography. So in this study, we did it in vivo, and it's a little blurry, but basically, if we just focus on these two groups, we can see the blue received the control. It didn't get the drug. The heart gets quite a bit bigger, and this is a pretty substantial difference in cardiovascular in the heart. But when we give this drug, the CDK8 inhibitor, it reduces that hypertrophic growth, so it prevents some of that what I'm going to term as pathological growth. And then when we look at the cardiac function, so how well the heart contracts by echo, we can see, again, just focusing on these two groups, the hearts are beginning to get sick. This isn't in the pathological range, but their function's declining in this group with the control. And then when we give the drug, the CDK8 inhibitor, we can actually reduce or prevent that loss of function. Then, because scientists, and we take the reductionist approach, we really want to know how it's working. So we looked at cardiomyocyte specifically, and I don't think you can see it with the lighting. So I'll just tell you what it looks like. So there's some red stains here, blue dot in the middle, and these are neonatal cardiomyocytes. And under normal conditions, they're size 1. We normalize to size 1. But then when we give them this drug called phenylephrine, PE, it causes them to get bigger, and these guys are about twice the size of the ones that weren't treated. But when we treat them with both PE and our this other inhibitor, we can see that blunts that hypertrophic response. So we can do this in vivo, and we can do it in a dish by targeting CDK8. And because, again, the CDK8 regulates transcription, this kinase submodule works as a team, we wanted to look at RNA transcription. And without getting into too much detail, this is a principal component analysis. Basically, all these in blue are our controls. So these guys were our double negatives. They didn't receive anything but the vehicle, the DMSO. These guys received the Senexin, the inhibitor, but not the stress of the PE. And then we compared that to samples that got the PE. So the PE causes this pretty hard shift to the right in the data set. And this is looking at a whole bunch of transcripts, of mRNA transcripts. But what's cool about this study was, so these guys shifted hard to the right. If we give PE and a low dose Senexin, it shifts it a little bit back to the left and down, but it shifts it really hard back to the left when we give a higher dose, suggesting that we're regulating transcription levels, and that's how the inhibitor is actually working. So this is just another example of a small molecule that we can use to target a component of the kinase submodule, the kinase specifically itself. So in conclusions, we do have mouse models of Med13l, and we're working to define the specific assays that we need to look at to test then the therapeutic candidates. And then that there's a lot of potential for the small molecule inhibitors that we can test in these preclinical mouse models. So with that, there's a lot of people that did the work. I'm not going to go through them independently, but I wanted to acknowledge them. And then if there are questions, again, feel free, to email me or ask me at the conference or when we're sitting up here. I'm always excited about answering questions.
Well, the first thing I'd like to do is thank the organizers and the families for the invitation to come here and speak. It's been, Chad and I were talking about this last night. It's invigorating when we talk to the parents and see the kids and things like that. It really stimulates us to get motivated to get back into the lab and do things. So in some respects, we may be giving you guys something to think about, but you've also done the same back for us, and we appreciate that. So what I'm going to talk about is something a little bit different than what Chad spoke about, although it's the same set of proteins. But I don't know if anybody was around in about 2005 when the human genome came out. You heard Chad said there's about 22,000 human genes. And the human geneticists were the saddest people you've ever seen in your life, because they anticipated, since we were the pinnacle of evolution, that we would have the most genes. We would have 60,000 genes, 80,000 genes. And it turns out we had 20,000, 22,000 genes. Corn has more genes than us. Rice has more genes than us. So how can that be? Well, how can that possibly be the case? And it turns out one of the ways that is we take care of that is by having proteins to do different things in different places. So as your realtor always said, location, 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 right? And so that's what we're going to talk about today, about the role Med13l and Med13 play in the localization of a protein. And that change in localization makes a big difference to the cell. So here's the CDK. This is a little bit different version than what Chad was showing. So this shows the parts of the CKM, the CDK kinase module. And again, as Chad pointed out, there's paralogs for CDK8, Med12, Med12L, and Med13, Med13L, and there's cyclin C. And we found, looking at mouse embryonic fibroblast and a cyclin C knockout animal or cell line, it regulates about 3,000 genes, about 50% up and 50% down. And I'm not going to talk about that anymore. So basically, what I'm going to talk about is cyclin C and a role for cyclin C in the mitochondria. So, which is not the nucleus where this thing normally works. So as you know, from your 9th grade biology class, mitochondria are the powerhouse of the cell, right? Everybody remembers that. And the other thing everybody remembers too is that mitochondria look like beans. So these are EM micrographs of mitochondria, and this is what everybody thinks they look like. And it turns out that's not quite right. In reality, when you look at mitochondria in cells that haven't been fixed for EM staining, they look like this. Now these are C2, C12 mouse myocytes. And so what you see is that the mitochondria are actually elongated and go out throughout the cytoplasm. And they're enormous. They have very intricate structures. And this structure itself is actually very important. So what the mitochondria look like actually has a big role in how it functions. So this is a mouse embryonic fibroblast. And in general, most of the mitochondria, again, are elongated like this. And that's important for when mitochondria are like this. This is basically when life is good for the cell. The the mitochondrial DNA repair and lipid repair is up in the elongated cells. ATP generation is up. So this is when life is good for the cell. However, it can change to a fragmented phenotype. And this fragmented phenotype is associated with the early stages of a process called programmed cell death. But it's also involved in a quality control mechanism called mitophagy. So the damaged fragmented mitochondria are picked up and taken away to be disposed of, like in a recycling type of mechanism. And also it's involved in cell division. So you have So you have the fused mitochondria being around when the cell wants to make a lot of ATP, and the fragmented mitochondria is usually in response to a stress type of situation. Now, what happens and why are we talking about cyclin C is now this is yeast, right? So this is the baker's yeast, or somebody may know it more as brewer's yeast. And this is where we first got our start in it. So we identified the CKM components, all of them, in a genetic screen in yeast when I was a postdoc back in 19. And so this is looking at cyclin C, which is in the nucleus here. This is in yeast now. And the mitochondria, just like I showed you in the mouse and human cells, are elongated. However, when you stress the cells with reactive oxygen, so oxidative stress, you see what happens to the cyclin C. It's no longer in the nucleus. It's now out in the cytoplasm, and you can see the way it's interacting with all the red spots and turning yellow. It's involved in, it goes out and binds the mitochondria. So this is the powerhouse of the cell. And we found that this release of cyclin C into the cytoplasm was involved and is required for mitochondrial fission and also required for programmed cell death in yeast. So this was an important discovery for us because it told us that cyclin C was doing something completely different than what it did in the nucleus out in the cytoplasm. So you got to wonder, so, okay, so where is required for this? So where's Med13? And so the first thing we wanted to say is, okay, is this also true for mammalian cells? So mammalians, vertebrates and fungi separated about 300 million years ago, according to evolutionary. I think it was like a Tuesday, wasn't it? Yeah, I think it was Tuesday. But this is, again, looking at a DAPI stain. So this is the nucleus of a mouse cell. The mitochondria, again, are elongated. Cyclin C is in the nucleus like a good transcription factor should be. And here's the merge. This is work done by a former graduate student of mine, Kun. And what happens when he added hydrogen peroxide, so this is an oxidative stress now to the cells, he sees now the mitochondria are fragmented, like I showed you, just like what happened in yeast. And what we see in, oh, I'm losing my battery. What we see here is in this next thing, the next panel over, is you see the cyclin C, some of it is out in the cytoplasm. And if you blow that up, this picture here up, you can see we get a localization of cyclin C with the mitochondria, just the way we saw in yeast. So 300 million years of evolution, these proteins do exactly the same thing. And so we wanted to take advantage of that. All right, thank you, sir. Now I gotta learn new buttons. Okay, so here you can see where the arrows are. This is the co-localization. And it basically does the same thing. If we stop cyclin C from getting to the cytoplasm, it doesn't do mitochondrial fission. So what does this got to do with Med13? Well, what we found was that, no, which way is it going? No, it's not going forward. That's working. I think I got the right button. Oh, there it goes. Are you doing it? I just raise my hand and do this. Okay. All right, thanks. So I still have the button now. So what's Med13 got to do with this? So this is back in yeast again. A former student of mine, Svetlana, she deleted cyclin C because what we found was that cyclin C needed to be destroyed. Our Med13 needed to be destroyed to allow cyclin C to get out of the nucleus. And so when she knocked out Med13, so this is a yeast cell that doesn't have Med13, you see cyclin C is out, instead of being in the nucleus where it's supposed to be, it's now out in the cytoplasm all the time. And the other thing we found is that the mitochondria were fragmented all the time. And then, as you can see, the co-localization here. And so what we found was that Med13 played a critical role, not only in tethering the CKM, the kinase module, to the mediator, but it also is required to keep cyclin C in the nucleus. And in response to stress, Med13 was specifically targeted for degradation. That allowed cyclin C release into the cytoplasm. And now you had the stress response going on. So it was about that time that I got contacted by this guy, Peter van Hasselt, the University of Utrecht in the Netherlands. And he had a patient with a Med13 mutation, which Wendy didn't have on her slide. We'll have to talk to her about that, this mutation here. And so basically had some of the general phenotypes associated with the Med13l mutation. And so he wanted to know, since we just published this Med13 paper, whether we thought we had any ideas what could be going on. And so the hypothesis we had, which was pretty straightforward, if you have a mutation in Med13l, you may not be able to allow cyclin C to stay in the nucleus. It may allow it to get out into the cytoplasm. So we tested that. We got a fibroblast cell line from this patient. Thank you. And so we did the experiment. So this is WI38. This is a controlled normal human fibroblast cell line in which cyclin C is in the nucleus. Here's DAPI, which is a nuclear stain. This is an antibody towards cyclin C, so it tells us where it is. The mitochondria are elongated, and here you can see a picture of it. And so what does the Med13l fibroblast cell line look like? Next slide. Thank you. So it's down here. So here again is the nucleus. But if you can see here, the green where cyclin C is, it's still in the nucleus, but there's a lot of it out in the cytoplasm. And instead of the mitochondria being elongated like they normally are, they're now fragmented. And cyclin C is out associating with the mitochondria, you can see with the white arrows. Now, this was interesting to us. Oh, back up, not just yet. This mine's working again. This was interesting. So one of the things we had found in a previous paper was there's a drug it's called PFT, which for short. And we know that this stops cyclin C from getting to the mitochondria. So we tested this drug to see whether PFT also affected mitochondrial fragmentation. So when we add this drug to the Med13 cells, you can see that we now restore mostly cyclin C back in the nucleus, and the mitochondria now look normal. So we think that the mitochondrial fragmentation is indeed due to cyclin C being where it's not supposed to be. So that's the aberrant thing. So we wanted to test this farther and do some more work on this. So even though the drug stopped cyclin C from going there, we had to be confident that the Med13l mutation, which was causing the cyclin C release, and it wasn't due to a secondary mutation. So this is something that you always have to do when you're looking at trying to correct a mutation, is understanding whether the phenotype is a direct result of that mutation or whether it's a secondary result. And so, did I do that or did you do that? No, okay. So we wanted to correct the mutation, and we used a CRISPR with the help of Ping Zhang, who was the head of our transgenic department. So here we have again the Med13l fibroblast. Again, the mitochondria are fragmented, and if you zoom in on this, you can see cyclin C, the green dots, out in the mitochondria, causing the mitochondria to fragment. So two different clones that we had that corrected the mutation, Med13 back to the wild type. As you can see, you get the restoration. Cyclin C stays in the nucleus, and the mitochondria stay elongated. So, like with rare base, if we have drugs that we can test to see whether some drugs are helping correct the Med13l mutation, this is our assay. So it's either this or this. So it's relatively straightforward to do. It's quick, and it's pretty definitive on whether this is working or not. The downstream effects, we don't know enough, but we'll be able to tell at least whether this drug is having an effect on this particular phenotype. Next, please. So one of the things we wanted to do when you saw the idea of mitochondrial fragmentation, what people have seen in other cases where mitochondria are constitutively fragmented, they tend to lose their mitochondrial DNA. So for people who aren't experts in mitochondrial biology, the mitochondria has its own DNA, and it's relatively small, and it encodes only a few proteins that are involved in the mitochondria. Most of the proteins in the mitochondria come from the nucleus. Okay, there's only a small subset of those, and they're critical for mitochondrial function. And what people have looked at, what people have found where they have cells that are constitutively fragmented, where the mitochondria are, mitochondrial copy number goes down. And so we just did this test, and I won't go into the details about it. We did this test, and sure enough, in the WI38 controls, we had a certain copy number, a little bit over 1,500, and about half. We had a reduction of about half of the Med13l mitochondrial DNA. And looking at that in another way, next slide, please. We wanted to look actually directly at the mitochondrial DNA, so nothing indirect. And so to do that, we used an antibody against DNA itself. So these green dots here are not cyclin C this time. These are actually the mitochondrial nucleoids, so the DNA inside the mitochondria. The red is still the mitochondria. And here's the control. And what you can see is where you see red, you basically see green dots almost everywhere. And in fact, 99% of the red mitochondria have a green dot in it. Okay, so this is the way it's supposed to be. And then when we stress the cells, the mitochondria fragment, and almost all the mitochondria have a green dot. There's a couple that don't, where the red arrows, but most of them do. So this is the way it's supposed to be. So now if you look at the Med13l mutant cell line, next slide, please. you see that a lot of the mitochondria don't have green dots. So here are the red arrows. As you can see, some do, but most don't. And if you stress the cells, it's the same story. There's a lot of the mitochondria don't have mitochondrial DNA. And so what that means is that the mitochondria, even though they're there without the DNA to encode those few proteins, they can't make ATP at a higher level. That's usually what that means. But we wanted to go and test that directly. So next slide, please. This is a former postdoc of mine, Kai T. And so he did an assay that we can use on the cell lines that measures mitochondrial function by looking at oxygen consumption. And so here again, in the blue is the WI38, that's a control, and the Med13l is in the red. And you can see we see a reduction in oxygen consumption, which means the mitochondria are not functioning as well as they should. Next slide. And we got a reduction also in ATP production. So that argues again that the mitochondrial function is not where it should be. Now, mitochondrial function is obviously an essential part of any cell type, any organ, but it's especially important for neuronal development and things of that nature. And the other thing mitochondrial function is critical for is skeletal muscle. If you look at cardiac muscle or skeletal muscle, it is chock full of mitochondria because that's where you need to make a lot of ATP. And so Peter van Hasselt in the Netherlands with his patient, he did a biopsy of the muscle, thigh muscle, and looked at enzyme levels. Next slide, please. And these are just some of the levels. And what you can see is that, what you can't probably see back there is that of the 14 enzymes they assayed, 8 of them were below the level they should be as far as the norms. So again, this argues that it's not that the mitochondria aren't functioning, they are, and there is ATP being made, but it's not where it should be, right? And so this could be read out as a phenotype with so an individual who can run, but they can't run for a long time. So the stamina is an issue, and other types of things like that with this kind of muscle. But it turns out this became very interesting to us because muscle itself, the way it's regenerated, goes through some very interesting mitochondrial dynamics on its own. So this is now, so next slide, please. So this is just pictures of mitochondria going through this differentiation process. And I know it's hard to sort of see, but when you start out, these are called myocytes. So these are just before they start differentiating, these happily growing cells. And what happens is that when you start the process, they start getting longer. I think you can probably appreciate that. By day 3 and by day 6, they actually start fusing into tubes that will eventually become part of your striated muscle. So this is how, when you work out really hard and you break down muscle, your body has to rebuild that muscle. That's how you get stronger. And so this is the way it helps rebuild the muscles, by activating this pathway here to generate more muscle fiber that gets incorporated into your full muscle. Next slide, please. This is just what a cartoon looks like. So cartoons are always better than real life, right? So you start with these myoblasts, they get elongated, and these red dots here are the nuclei, and then you form these multinucleated cells. So but the thing that we were interested in with this myocyte, this is something that's been documented a long time ago, is the mitochondria go through some very interesting dynamics during this process. Next slide, please. Next slide. Okay, thank you. So under normal growing cells, those myocytes, the mitochondria are normal, quote unquote normal. Although they're not very functional, they have a lot of dysfunctional mitochondria in them, but in general, they're okay. When you start the differentiation process, it goes through a fragmentation, the mitochondria do. Just like I showed you before with the stress, the mitochondria fragment, and that's critical because during this period when the mitochondria fragment, this is where this mitophagy or this quality control mechanism kicks in. And so any damaged mitochondria, which are indicated by the small little guys here, are now taken away, right? And the only thing that's left are good, solid, functioning mitochondria. And those are the ones that proliferate later on when the cell starts making the myotubes. So you need lots of mitochondria, lots of active mitochondria, And so the cell wants to get rid of the dysfunctional ones and make sure it only is using functional mitochondria. So previously we've looked in yeast and we've looked in mammalian cells, human cells. We've always seen the same thing as cyclin C gets relocalized in response to cell damage, whether it's an anti-cancer drug or an oxidant, something. But we've never seen it move in response to a differentiation cue, which is what this is here. So, but we wanted to see whether this fragmentation that happens here, does it involve cyclin C? And kind of next slide, please. So, oh, that's fine. So here's day 0, and this is these myocytes. And so you can see that the cyclin C is in the nucleus and the mitochondria are elongated. But by day 1, you see release of cyclin C. Can I have next slide, please? There's a blow up of this. And so what you can see is now cyclin C is now out, just like it was in the Med13l cells. And it was out in the cytoplasm, causing the mitochondria to fragment. And then next slide. Next slide. By day 3, cyclin C is back in the nucleus, and the mitochondria, and now next slide, please, now start forming normal mitochondria for the muscle strength, right? So this is for muscle development. So this argued that cyclin C going out into the cytoplasm was important for muscle differentiation. And so you remember that drug we used earlier on, this PFT drug, which stops cyclin C from getting to the mitochondria. Then next slide, please. Here's what happens when we take these same cells, and half of them we just did this with it. The other half we added PFT to stop. So cyclin C got out into the cytoplasm like before, but I think you can see the difference between here and there is that the mitochondria aren't fragmenting. Cyclin C is not getting there well enough to do that. As a matter of fact, it stays hanging around for a couple extra days because it can't figure out what it's supposed to be doing. And then finally it goes back into the nucleus at day 7. But the problem here is without this mitochondrial fragmentation, the final event of myotube formation is now defective. So you get less efficient myotube formation because these mitochondria aren't correct. And it turns out that we have a drug that can mimic sort of Med13l syndrome in that we can add it to the cells and it will cause cyclin C release into the cytoplasm. I don't have the data here. It's still just happened. And so it looks like, again, if we add this drug, we can cause, next slide, please. It'll cause cyclin C to go out into the cytoplasm, but it will actually induce fission. And it keeps the mitochondria fragmented as long as we keep the drug on it. And that in turn also causes a defect in what we can sell so far in myotube formation. So for muscles trying to regenerate themselves or just in growing, aberrant cyclin C in the cytoplasm seems to be a problem for the cell to be able to understand how to do that, right? So that's what we're working on right now. Right now, we're taking these cells that we can do this with. We're knocking out cyclin C, which I think we just got, but we're also going to make a Med13l mutation that mimics what we see in the human disease, and see what happens to muscle development and things in that nature. It's not neuronal, right? So that's, I mean, obviously that's the focus of a lot. We're not neurobiologists, so that's okay for us. But this gives us a nice readout for Med13l function, and it could explain some of the mitochondrial defects that people may be seeing with their children, and our loss of mitochondrial function, and perhaps some of the muscle issues that people talk about every once in a while, where strength or stamina has been reduced. Can I have next slide, please? So I don't want to make you think that what Chad was telling you about Med13 controlling transcription was all worthless. It's not the case. It's not all worthless, but no. So when we did our genetic analysis of the cyclin C knockouts, where we found a bunch of genes affected, a lot of those genes were involved in mitochondrial maintenance. Remember, I told you that the nucleus encodes lots and lots of genes for proteins that go to the mitochondria. That's what makes up the mitochondria. And so a lot of the genes that cyclin C that was required for their transcription were involved in mitochondrial maintenance. And so what David Stieg, a former graduate student, did is, next slide, please. He took those Med13l mutant fibroblasts, and we looked at those specific RNAs that were downregulated in the cyclin C knockout. And sure enough, although the amounts are not great, this is log 2. So this is basically at 1, it's twofold down from where it's supposed to be. And these are pretty abundant genes. So it's not that we've lost mitochondrial function again. There's proteins are being made, but I think that the next slide, please. What we're seeing is that, there we go. There's two things going on for Med13l control of mitochondrial function. One is the transcription part of it. So we're definitely not seeing normal transcription of genes involved in the mitochondria. And it's also the morphology part, with cyclin C being aberrantly out in the cytoplasm, causing that fragmentation to happen. And so with both of those things going on, that's why we think that mitochondrial function may be reduced in the Med13l fibroblasts. Next slide. So here's my model. And that is under normal conditions with wild type Med13l, cyclin C stays in the nucleus where it's supposed to. It induces RNA polymerase transcription of mitochondrial maintenance genes. And both of this combined, the cyclin C being absent and these genes being expressed, you get normal mitochondria that are fused, producing a lot of ATP, the integrity is great, and have lots of mitochondrial DNA. Next slide, please. In a Med13l mutant, what we're seeing is that we see a partial release of cyclin C, and that's causing fragmentation of the mitochondria, but we're also seeing reduced mitochondrial expression of mitochondrial maintenance genes. And that's also probably affecting mitochondrial function as well. So it's sort of a double whammy on this. And so, like I said earlier, what I haven't said yet is one of the problems that we have with this study so far is this. We have an N of 1. So we've done one cell line with this, and this is what we found. We don't know whether this is a common thing, whether this is a very rare thing, whether it only happened for this particular mutation, which is probably doubtful, but still we don't know. And so that's one thing that the Simmons group, Searchlight group, we're involved with them and also with families here to get more samples to test this, to see whether this is a common feature, this thing here, or whether this is not. So that's an important thing to do before we go too much farther, is find out just how often this occurs. And next slide. So what I want to end with is something that Chad touched on, and that is this complex. As you can see, it's very involved. You got 4 proteins that are stuck together in a variety of ways. And what Chad pointed out, and I'm just going to reemphasize this, is that it's not simply Med13l that has these intellectual disability mutations, right? The mutations in Med13l. Mutations in Med13, Med12l, Med12, CDK8, or CDK19 have also shown a not identical but overlapping pattern of symptoms with the kids. So this would argue that perhaps that this is a wider group of maybe not identical but more common types of issues, that this would make the community quite a bit larger, being able to incorporate this and being able to, on the molecular level or biochemical level, be able to connect these diseases together makes us a lot more important to things like the NIH and things like that, because now we're not talking about a handful, we're talking about a significant population. So this is one of the directions that my lab is going to be going in addition to verifying the Med13l story and making sure that that's right, is also identifying and getting additional mutations in our cells with mutations in these different other ones, and seeing whether this holds up or not. Okay, whether this is actually, there's commonality between these different diseases. Next slide. So if anybody wants to buy me a beer, slide back, please. Slide back. The protein that's missing from this, the gene that's missing from this list is cyclin C. And cyclin C, it's interesting because doesn't have a paralog. There's not 2 of them. There's only one, cyclin C. So you figured that if a mutation in any one of these genes would cause a problem, you'd figure cyclin C would be the most obvious one, right? Because there's only one gene, so there's nothing else to help it. But they don't find mutations in cyclin C in this thing. So if if you want to see me afterwards, it's a little bit long-winded, and I would probably have to have a beer to describe this. But we can talk about why cyclin C is not in this thing and how that may be telling us something about the whole Med13l business. Okay, final slide, please. And these are the people that work, my collaborators. Peter from that got me started on this. And then actually shortly thereafter, I contacted and Kelly, and then we started the conversation back and forth. And this was just something, an oddity that we were just going to touch on in my lab. We were going to see whether this was true or not and move on. Most of the people in my lab work on cancer, pancreatic cancer. So we don't, this is something that's now taken over. At least half of my group now is working on the Med13l story. So this is something I've just recently come to, but I've become very passionate about it. So we're very excited about the work we've got going. And so these are current lab members. Alicia did the studies with the muscle cells. And so she's the one that's carrying that on. Former lab members who had a big role in this and a variety of funding sources. So thank you very much.
Okay, I think maybe stay on the stage if that's okay. We'll have some Q&A. Would you like to join him? And then if any of our families have any questions, just come up to the mic or I can bring a mic to you. Anyone have any questions? Yeah, of course. Whatever you want to do, a question or you can sit up. Yeah, go for it.
So think about translating the work you're doing, starting to think about into therapies. It'd be great to hear your thoughts on follow-on work in your respective labs. It was most important and stepping stones to help support bringing therapies into the clinic.
No, I think anyway, I think what yeah, people can hear me. I think the big issue with generating a mouse model of Med13l is how do you identify it? How do you assay it? How do you see whether it's a faithful model of the human situation? And so I think what we're going to focus on is this aspect of it. So we've got a nice concrete phenotype that we can measure, looking at whether the drugs that are available, whether the mouse system that's being developed, whether this recapitulates what we see here. So I think that that's going to be one of the things that we're going to focus on with all the tools that are now available.
And when you think about phenotyping the mice, to what extent are you focused on biomarkers versus symptoms like intellectual disability is expressed through certain mouse or even other animal model studies?
Well, for us, the understanding the neurological problem is, I mean, it's obviously that's sort of the place where everyone wants to get to. I think understanding what the possible defects associated with Med13l are, whether it's transcriptional, whether it's in the cytoplasm, or whether it's both. I think understanding what the contributions of those two different systems are to the overall disease is going to be important for understanding which therapies are going to work the best and which therapies will work okay, or do we need to understand both of those systems, the cytoplasmic and the nuclear role, and do we need to target those independently and then eventually use a combination of therapies?
And sorry, one last question, and this is going to be for both of you. Can you then describe for the audience what resources would go into the work that you're describing in terms of just allocation of time and people and other expenses to what you're describing?
Well, it turns out that the work I showed you here hasn't actually been supported by anybody yet. So we've sort of borrowed off other grants of support to do what we've done to this point. And we're writing grants now to get this, but the allocation is going to depend on the support, right? To the how much money we have to put into people and reagents and things of that nature. So right now, I mean, we're on a sort of a minimal budget because we're borrowing from other sources. So it all depends on how quickly we can ramp up. As one is the collaborations we can identify and have other people to help us with some of the things. But the other thing is this, the support we can get from outside the extramural sources.
So I'll put a little bit of money, dollar signs to it if you would like. So for my mouse colony costs, I spend $3,000 a month on I spend $3,000 a month on mice alone. That's just to maintain them. That's not doing any experiment. That's just to have them housed downstairs in a controlled environment. So just that alone, and that's operating it, within the margins. I too don't have direct funding for the Med13l. That's why there's less. I piggybacked it with the Med13 project that I had, and I didn't show you near all of the data for that. Right now I'm piggybacking it on CDK8 project that I just showed you. So as Randy showed you, and hopefully I showed you as well, these complexes work together. So it's justifiable in my mind to piggyback them. To do what I would like to do in the next 12 months, it would require a full-time postdoc or student to really make the significant progress. That being said, we'll make the progress no matter what. Hours wise, I can't, it just depends on, as a postdoc, I worked 80 plus hours a week. So it just depends on the individual. And that 80 hours a week was that little cartoon with the fat mouse and the skinny mouse. That was, 6 years of work right there, and a very highly productive lab, and a lot of money, a lot of effort. So it takes a lot of years, typically. The progress that's been happening in the last 12 months is actually, to me, phenomenal. Even though, I think it's just getting started. So.
Well, it was 6 years, but I mean, at your stage in your career to have published in Cell is pretty remarkable.
It helped. Yeah, it was a good start.
So really same question for you. What experiments would you like to conduct as important stepping stones to help us develop therapies?
Yeah, so as Randy pointed out, the most critical thing for me, like in the lab for the next 6 months, is to define the assay in the mouse that's reproducible, that we can translate to humans. So I showed you there's a growth delay. And then some changes in transcription, and that's about as far as we've got for the phenotyping of these guys, these mice. What I really need to know from these mice is, can we, and the experiment I'm really excited to do is the forced running. So do these mice do they have less endurance? That if that's the case, that one's easy for us to test in the lab. And then that's an easy one to modify, easy relative, right? To modify and see the outcomes, because it doesn't matter how good your small molecule is at answering your question if you don't have an assay that can test it. It may be wonderful at doing its job, but we have to do our job and be able to define how wonderful it is. So that's our biggest gap right now, is defining that assay. So we have the mice. We have the mice we need, at least, and I'm willing to share, I have the mice at least. But that assay is the critical next step.
It's so interesting because one of the things that we're trying to do is map the assays that you're describing to endpoints in clinical trials. And if we do a clinical trial, you have limited funding, and let's say you have funding for 12 weeks, there's virtually no chance you're going to be able to show, for example, improvement in speech development in that short period of time. That takes longer. But if you can improve the function that you're describing, and you can show improvement on stamina tests, where they're very well understood and FDA appreciated endpoints and tests, then we actually have a shot of showing which drugs may or may not be valuable in the short term.
They might not address the immediate concerns of the population with the speech and stuff, but if it shows efficacy in one assay, then we can justify the other assays as well. So I agree.
Please, no, please.
Besides money, which obviously was on the top of my mind. So I was a chemist, bench chemist for 20 years. I know that it's time, effort, money, people, all of that, but also interest. So as family members, how do we keep you interested in sticking with this project?
Give
I
us
mean,
money.
I know money, I know. I got that. Is there anything else? I mean, is it meeting with you regularly? Is it coordinating different collaborations? Okay. All right, so we can scare you, but if there's anything else that the family members, you know, we're trying with the money, we're raising as fast as we can and as much as we can. But
So,
how do we keep you interested? Like, do you want to hear the stories of the families more? Do you want to meet with us more regularly? Examples?
Biopsies, things like that, so skin biopsies, blood samples, things that we can use to hone the assays, to understand. That'll do two things for us. One, because of right now, as Chad pointed out, there's no obvious hotspot for mutation, why they're causing it. There's no obvious mutation, and this is a hotspot for where these mutations go. So it doesn't give us a good idea functionally on what it's doing and how to use those mutations to be predictive. So in other words, when somebody else gets diagnosed with Med13l, we'd like to be able to look at those mutations and say, this means that it's going to go in this direction, or it's going to go in that direction. So the more samples we get from families for us to assay, and again, the Searchlight group, Simon's is doing a great job with helping get that organized. That's going to be the tools that we need. We've got some of the assays developed. Chad and I have got some of the assays developed that we could work on now. But I think and obviously we met once a year, as I mentioned when I first started talking. It's really energizing for us to come and talk to you people. So, and see everybody, see the kids, see the families. So this is the first time I've ever been in a meeting like this. I've only gone to meetings with other scientists, right? And so having families here in the whole idea of this type of situation, I think is perfect. And I think it should be continued.
That's what I was thinking. And I know regularly, you know, once a year is probably pretty good because the time it takes to accomplish anything in the lab can be a significant amount of time. So, you know, quarterly updates, you might not be getting a lot every quarter, but when you put it all together at the end, you know, so maybe we could do that, just continue yearly. So we know the money, we got that. And that's scaring you. So we'll just keep reaching out and making sure that you're not forgetting about it.
So I will also say that Med13l was a side project for me because I had funding in other areas, and it was interesting because it was a homolog of Med13, and that's what I started with. I was honestly going in a different direction until about, October when we had our first meeting, and I can tell you it reinvigorated my career. I'm always excited. I'm a science geek anyway, you know, so you're not going to get me in the lab more. You're not going to get me reading about this more, or the meat eater complex, but I'll focus on Med13l in my assays. I'll develop specific assays. So for example, one of the reasons why it's taken me a little longer than I'd like with the Med13l mouse models is because I bred it right off the bat to Med13 because I wanted to knock out all 4 alleles and study them because I was less interested in Med13 as opposed to the whole concept. But now I had to breed it back down to the Med13l by itself. So this group, it did change my trajectory as far as studying Med13l, and moving forward, I don't need motivated. I've already got the motivation. I mean, I love it. I love seeing, you know, the support. That's amazing. But
come and go, or your students or your lab techs, maybe us coming to you and telling them how important it is to us. We would be happy and willing to do that. I think that personal connection, at least in my line of science, has always been really important. And it makes you say, okay, you're doing something important. Somebody's really listening or paying attention. I think that's important. So we want to keep you engaged, but we want to stay engaged. You have to let us know what else we can do besides money.
Yeah, thanks. Yeah, I appreciate that as well.
Wanted to, if you don't mind, tie what you were describing to an initiative that we have here. We have phlebotomists here to take blood on Sunday morning. And part of the assays that will be done with that blood is studying a wide variety of proteins. So 7,000 proteins. And it's interesting to hear that 3,000 proteins are either upregulated or downregulated by Med13l, and that a lot of those relate to the mitochondria. That's one of the reasons that what we're doing here could, I think, be quite valuable. It'll give a sense of whether or not that upregulation and downregulation signature is consistent in our patient population. So it's just, I mean, I'm not sure there's a question in what I'm saying, but it's kind of a public service announcement to kind of tie what we're doing to.
No,
to what
it's
you've done.
actually, yeah, no. It's real. Yeah, can you hear me? Okay. No, I think it's really important because, like I said earlier, we don't know whether this mitochondrial defect is something that's a more general problem or not. So if you can generate a profile and then we can tie that profile back to mitochondrial function, that makes it so easy. Then at that point, then we go forward with understanding we've already got this profile established. So now we can deal with the actual patients and things like that at that point and not have to go through all the assays. Because no, this would be not only that would tell us maybe what's going wrong. Yeah.
And then the other thing we were talking about today at lunch, just for everybody's edification, is there is a facility that that Simons and Dr. Bain would make accessible to us where we can give skin biopsies, and those can be quickly converted into the types of cells that Randy needs for his research, which will allow him to go from one cell line, one patient, to hopefully many dozens. So I think we're going to try to organize that for September for whoever's able to be in the area. But that could really, we hope,
Yeah.
accelerate work.
So this is New York. So in the New York area. So yeah, that would be great. And so the like I said earlier, the getting the more numbers we get, it'll allow us to maybe be predictive for future patients, and also give us a clue about how this Med13l is functioning and how it's not functioning and how it's affecting both the transcription, the nuclear part, as well as the cytoplasmic. So it's definitely a more of the merrier type of situation. Yeah.
So I want to come right back to another thing I just thought about for your question. So, or your statement about what could get us excited. So one of the things that's been huge is the collaborative effort. So there's no way as an individual who, was just getting started, I'd had the rare base, looking for this small molecule screen. That's a step beyond my expertise. But, I'm hoping to have the opportunity to go through that list and test them in the mice, the hits. So that makes it drives my personal, we all research a lot farther, a lot faster, working with Randy. So I'm following his coattails on the cyclin C stuff in the heart. It works in the heart. So I was able to do that a lot faster because of his work and collaborating with him, learning from him. So generating those mice, those are things that, as an individual lab, it's possible, but it would take a lot longer for us to do that. And you guys driving that really makes it, super exciting, because now I got a lot of tools and fun stuff to play with later. So it's awesome from my standpoint.
There's a saying in real estate, it's all about location, location, location. Our mantra is it's all about collaboration, collaboration, collaboration. And seeing the way you all have been collaborative is fantastic, and collaborative not just with other researchers, but with the patient community.
Okay, any other questions? Any for the family members? Okay, we want to thank Randy, Chad, Nick, and Wendy for the presentations. And just a few items. We have our 4:45 group picture just outside. So make sure you go get your family members, your kids, and join us out there at 4:45. And also Searchlight asked if anyone did not fill out the photo waiver yet, if you could just stop in the back and kind of fill that out for the release. Okay. Thank you for your participation. We really love having you all here, and thank you.